GD&T is a language of symbols used to communicate design intent. Now I've identified 4 major concepts that I'm going to cover in this video that's going to help you with your GD&T studies. The concepts are 1, datums, 2, feature control frames, 3, material condition modifiers, and 4, basic dimensions. If you know what these are, you can identify them and you can apply them to a drawing, you're going to have a pretty good handle on how the system works. Let's get started right away with datums. Now, the definition of a datum is that it is a theoretical point, line, or plane. Now, we can't touch or measure something that's theoretical, so we identify features on the part to serve as datums and simulate them with datum feature simulators, which are just inspection equipment. Whether it's a surface plate to simulate a plane or a gauge pen to simulate a cylinder, we're just going to get as close as we can to that theoretical perfect datum. Now, the other way to understand datums, which is very, very important, is that datums are places to measure from. Let me give you some examples of what I mean on the board. So I've got 2 drawings on the board. Let's talk about this one first. We've got a stepped block with a leader directed note that indicates parallel to 5 thousandths. Now, this is definitely not allowed anymore, but if you look at drawings that are, 50, 80 years old, you might see something like this. This is what's known as an implied datum. It's up to whoever is interpreting the drawing to decide what this surface is supposed to be parallel to. Now, you might say, duh, it's this large surface down here, and you'd probably be correct. But somebody else could say, hey, I know how this part functions. It actually fits upside down. That surface is supposed to be parallel to that surface, right? So what datums do is specify exactly which surface something is supposed to be oriented to or located from. Let's go into our next example. We've got a block with a hole in it. Now, we've got a center line going through the block and then 1 dimension covering the height. This indicates that that hole is centered in the middle of the block, okay? So that center line and then that dimension indicates this. We don't need another dimension for the location of that hole. But one person could say, let's measure from this surface, make it 1 inch plus or minus 10 thousandths. Another person might say 1 inch plus or minus 10 thousandths from that surface. Another person might say, well, why don't we take the block and put it in a vise and then find the center, right? Simulate that center line and then get the location from there. Now, none of them are really correct, right? Plus or minus dimensioning really doesn't have rules for how to do this stuff. You're leaving the interpretation up to whoever has the drawing, who's making the part, who's inspecting the part. What datums do, we can identify this is a datum and clearly state that the center of this part is a center plane datum and then the hole is located from the center of the part. It's all about being explicit about the drawing requirements. Now, we'll talk more about datums as we go through this talk right now, but this is good enough for now. Datums are places to measure from. Next up, let's talk about feature control frames. Now, this example here, I've just written it out in a note, and that was the way to do it. Older drafting manuals would just spell things out. Hey, make this cylinder concentric to this cylinder. Make the total indicator read out this. Everything was written in notes. The problem with notes is that it leaves room for interpretation. Think about if you ever took an English class and you're reading an essay, your teacher expects you to interpret it, but they know every student isn't going to interpret it the exact same way. So notes should be as short as possible. That reduces the room for interpretation. But if we can use symbols instead, we further reduce the room for interpretation. So to make this into a proper GD&T callout, we're going to use the feature control frame. Right? So feature control frame is a box. In this case, it's leader directed. The very first box will have the geometric characteristic symbol. The next one will have the tolerance. After the tolerance will be the datums. In this case, with this particular tolerance, we only need one datum. We're going to write our datum feature symbol down here, connect it to the bottom surface. So now it's explicit what the drawing requirements are. Okay? So next up, let's talk about feature control frames. Now I've replaced the note on this drawing with a feature control frame that accomplishes the same thing. The first symbol is the geometric characteristic symbol, then their tolerance, then our datum references. In this case, we're just saying that this surface is parallel to 5 thousandths to datum A, which is this bottom surface identified with the datum feature symbol. Now, let's move on to a couple more examples of feature control frames. So feature control frames differ depending on how they're applied, what geometric characteristic is applying, and how many datums there are. Now, there's more videos I've made about this, specifically the different kinds of geometric characteristic symbols, but let's just talk about a few. First is form tolerances, like flatness, typically don't or never have a datum reference. Because form tolerances only apply to individual features, there's never a need to relate them to anything else. So in this case, a flatness tolerance is directed with a leader to a surface. It's just saying that surface is flat to within 10 thousandths. Next up, we've got a profile, which is very tricky. Profile can do a lot of different things. It can function just like flatness, or it can locate surfaces. In this case, a datum reference to datum A, it's doing the job of flatness, parallelism, and locating a surface if we have a basic dimension. And then another form tolerance, straightness, applied to the surface of a cylinder. This controls the line elements around the cylinder. Very simple feature control frame, just the symbol and then a tolerance. Okay? So let's talk about something a little bit more complicated. We'll get into position, which generally have the most complicated feature control frames. So allow us to talk about all of the elements of the feature control frame. So here is about as complicated as a feature control frame can get, but it's not too bad. So we've got a block with a hole in it. We've got basic dimensions locating the center of the whole feature. We've got 3 datums, so A, B, and C on perpendicular surfaces of the part. We're leader directed to a size dimension. Now, position is almost always applied with a directly toleranced dimension that applies to a feature of size. A feature of size, real quick, is something you can measure with opposing points. So this width of the block we can measure with opposing points. This hole we can measure with opposing points. Okay, so quick definition of feature of size. So our feature control frame, like I mentioned, the first block is the geometric characteristic symbol. The next block is the tolerance and associated adjectives to the tolerance. So in this case, with position, we have a diameter symbol here to indicate that the tolerance zone is a cylinder. So you can imagine there's a cylinder centered where these basic dimensions terminate of 30 thousandths. That's where the axis of this hole must lie. Next, we have a material condition modifier. In this case, it is MMC. This just means that as this hole gets larger, more locational or positional tolerance is allowed. And I'll put a card up. I made a whole other video about it. We'll just gloss over it for now. Next, now this is important, are datum references. Most of the time, they will be written A, B, C because it's a popular choice for designers. It makes it easy to read drawings because people are used to seeing it. It does not have to be A, B, C. It's in the order that the part is set up for inspection. So datum A should be a mating surface, the largest and most important mating surface. Normally, for a block like this, it would be one of the largest planes, right? That gives you good repeatability for inspection. Doesn't have to be. The second one is our secondary datum, typically the second largest surface, but it can be other kinds of features as well. It could be a feature of size, like a slot or a cylinder. So we could switch this. It could just as easily be ACB. In this case, we'd set up to A, B, and then C, okay? So they are in order, and it does matter. It's known as primary, secondary, and tertiary. Some people know this as the 3-2-1 rule. So 3 points for the primary, 2 points for the secondary, 1 point for the tertiary. The idea is to completely immobilize the part in all 6 degrees of freedom when you're inspecting it, right? It's stated on the drawing exactly how it's supposed to be set up for inspection. Again, this reduces errors in interpretation if everybody is trained up on how to apply and interpret GD&T. So now let's move on to material condition modifiers. This seems to throw people for a loop, but it's a simple system when you look at it. We've got 3 material condition modifiers to worry about. MMC with its little M with a circle, or written MMC, or spelled out as maximum material condition. Next is LMC, L with a circle, or LMC, spelled out it is least material condition. And then I put the symbol here. It's an S with a circle. Currently, the symbol is not used, and it has not been used since the ASME Y145 1982. But some people still, are comfortable with this symbol in notes and things. So it's spelled out as RFS. We've talked a little bit in previous videos about the concept of MMC. It simply states that external features at their maximum material condition are at their largest size. So if you have a pen that's plus or minus 40 thousandths, the MMC is 1.04, the largest pen. It's the opposite for internal features. So if you have a hole at MMC, it's the smallest the hole is allowed to be within the limits of size. It's a great way to compare whether parts will fit and how much allowance is between them. Another way to think of it is that the MMC is the heaviest part. So the largest pin is the heaviest pin. The smallest hole creates a heavier part than having a larger hole. Now, LMC is the opposite. So the LMC of a pin is the smallest it's allowed to be. The LMC of a hole is the largest it's allowed to be. We generally split these up into internal and external features. So the pen would be our external feature. Whether it's a pen, a block, or anything else, it's external. Internal could be a slot or a hole or a groove or any number of different kinds of features. RFS does not have a symbol because it is the default requirement for feature control frames applied to features of size. So what's a feature of size? I talked about it a little bit before. Let's go in a little bit more depth. A feature of size is something with opposable points that can be measured. Let me give you some examples. You have a block, the width dimension, that is a feature of size. If you have a pin with the diameter dimension, that's also a feature of size. It can be measured with 2 points. Same thing with a slot or a groove. That would be a feature of size because you can measure it with 2 opposing points. So think about a caliper, the inside measuring part of a caliper. What is not a feature of size is something like this radius, right? You can't get 2 points on that radius. Now you could make an argument that, okay, if the center line is the radius is on the same plane as the top of this part, you could. The problem is you got a tolerance on that radius. So if the radius comes in small, then you can't get 2 points. If it comes in large, maybe you can, but you wouldn't want to call that a feature of size. Next, something like a chamfer, not a feature of size because you can't measure out into air with two opposing points. Same thing with this open cut right here. That would not be a feature of size. So it's important to understand what is and isn't a feature of size to know what material condition it can apply at. So things that are not features of size cannot have material conditions. You can never have more or less tolerance than stated for something that isn't a feature of size. Now, let's talk a little bit about what these symbols do in practice. So, I've got a pin with a size dimension and a straightness tolerance applied to the derived median line. This just means, real quick, that the center of that pin must lie within a cylinder that is 20 thousandths in diameter, and that's all we'll worry about for now. So, there's no MMC or LMC symbol, but it is a feature of size. In that case, regardless of feature size, the one where we don't use the symbol applies. It is the default requirement. This is known as rule number 2 in the ASME standard. So all that means is that no matter what size this pin comes in at, there's always 20 thousandths of geometric tolerance. So pretty straightforward, right? It's exactly what you'd think it would be. Now, let's try the MMC modifier. So if this tolerance applies at MMC, it's best read as that it applies only at MMC. 20 thousandths only at MMC. So let's write that right here. When the pin comes in at 1.02, the MMC of this size, 20 thousandths of tolerance is allowed. But if the pin comes in toward its LMC, so it comes in smaller, more geometric tolerance is allowed equal to the difference, the MMC to the actual size. All that means, if it comes in 10 thousandths smaller, you get 10 thousandths more geometric tolerance. Simple enough, right? Same thing, we just keep going down the list. If the pin comes in at its LMC, you're allowed 60 thousandths of geometric tolerance. That's also equal to the total size tolerance, 40 thousandths, right? So we just add 40 thousandths to the 20 thousandths to see the total amount of geometric tolerance that may result if the pin comes in toward its LMC, okay? So let's try the LMC modifier instead of the MMC modifier. So now we read this, so we have 20 thousandths of geometric tolerance only at LMC. So we'll reflect that right here. If the pin comes in toward its MMC, you get more tolerance equal to the difference. So if the pin comes in at 0.99, you get 30 thousandths, 1.0, you get 40, and so on. So LMC is just the reverse of MMC in this situation, okay? So RFS is default for geometric tolerances applied to features of size. MMC and LMC can be used to allow more tolerance depending on the actual size the part comes in at, okay? Let's move to another concept, which might be a little advanced for a video like this, but let's go ahead and tackle it. Let's talk about datum feature material boundaries. These are known as MMB, LMB, and RMB, which sound a little like, MMC, LMC, and RFS. They're the same thing, but they're for the datums. So let me get this drawn up on the board. So I've got a drawing on the board here. We've got a donut shape with 2 dimensions applied to it. The outside diameter is identified as a datum with a size tolerance 2 inches plus or minus 20 thousandths. The MMC of that feature is 2.02, the largest it can be. We've got an internal diameter with a size tolerance and a position tolerance. So we're positioning the smaller hole to the outer diameter. The feature control frame, position, diameter tolerance zone, 0 at MMC. This just means that if the hole comes in at its smallest size, it has 0 positional tolerance. But if the hole comes in any bigger, you get more positional tolerance, just kind of like the chart we were doing before. Datum A is our primary datum, so we've got to establish 3 points of contact with datum A here. But datum B applies at maximum material condition, or MMB, maximum material boundary. What this is an optional inspection technique. You don't have to do this. You could inspect it with a closing shape, just like an RFS inspection. But you could also measure it with a fixed gauge. So what this says, what this is saying, is that you can check it at the MMC or virtual condition of this feature. So the MMC is 2.02. You can make a gauge for this part and check it that way, right? You're saying the inspection here is fixed. So what would the gauge look like? The gauge would be a ring with a pin in the middle, the ring to simulate datum B at its MMC, so it would be set to 2.02 inches, the maximum material boundary. The pin would be set to the MMC of this feature, so 1 inch plus or minus 20 thousandths. We would simulate it at 0.98. So if the part fits in that gauge, we've established that it has not violated this boundary. Okay, now all we'd have to do is check and make sure the hole wasn't too big. Okay? So these aren't always used, but they are a technique to save, money at inspection. If you can set your dimension or your tolerances like this, you can automate inspection to a pretty serious degree, right? You could have a robot drop this washer, this donut, into a gauge, and if it fits, it's good. If it doesn't fit, it's bad. It goes in a different bucket, okay? So that is a brief introduction to material condition modifiers. Next, we'll move to basic dimensions, which is mercifully simple, and it'll be the last thing I talk about in this video. So basic dimensions are theoretically exact dimension values applied to size or location of features that are controlled with a feature control frame. It's very important that basic dimensions are associated with a feature control frame. So in this case, I've just given the left-right basic dimensions, but these basic dimensions show you where the tolerance zone should be for this position tolerance. Another example are things like profile that control the location of surfaces with basic dimensions. Now, since basic dimensions are theoretically perfect, they don't count in a tolerance stack up. So they can be written differently than plus or minus dimensions. So if you did a plus or minus dimension like this, you could have a lot of stack up. With basic dimensions, as long as they connect together, you can interpret them. You can interpret the distance from the centers of the holes as 1 inch. Okay. Now, at inspection, you really shouldn't indicate the tolerance or the actual dimension for basic dimensions. Okay, so all of these dimensions here are associated with either this position or this profile. That's where the tolerance for the basic dimensions is. And the last thing about basic dimensions is that they must come from datums. That's where you're measuring from. The basic dimensions have to lead back to datums. Now they can loop. So datum C is here. We can go 2 inches and then back and then locate this, but they've got to be connected. Okay. So that's it for this video. I just wanted to go over these 4 major concepts of GD&T. I hope you got something out of it. If you enjoyed the video, please like and subscribe. Leave a comment down below and stay tuned for more videos like this coming soon. In this video, I'm going to talk about GD&T form tolerances. So there's 4 form tolerances in the current ASME Y145 standard: straightness, flatness, circularity, and cylindricity. And I'll talk about them in order. I'll give you the definitions, show you what they should look like on a drawing, and try to give a couple of examples of what each one is for. So let's dive right into straightness. So straightness does what it says it does. It controls the straightness of line elements. Now, there's 2 primary ways straightness gets used. It can control the line elements on a surface, whether it's a rectangular part, cylindrical part, or a conical part. It can also control the straightness of a derived median line for a cylindrical part. Now, they're 2 very different meanings, but luckily they're very distinct on a drawing as to how the feature control frame is applied. So let me give you some examples of each. So on the board are a couple of examples of straightness tolerances applied to different kinds of features. So the first, the straightness is applied to the top of a rectangular part. So we've got a size dimension that controls the location of this surface, and the straightness tolerance just refines the form of the surface. Now, straightness tolerances only apply in the view you can see. So this tolerance, the straightness, controls these lines in this direction, so parallel to the viewing plane. What that means is that on the right view, so front view, right view, okay? On the side where the straightness doesn't apply, you can use the full size tolerance for that feature. So you can end up with like a corrugated roof shape. So it's got to be straight in this direction, but not in this direction, okay? This can use that full 80 thousandths of size tolerance. Now, rule number 1 applies when it's applied to surface entities like this, so that 10 thousandths straightness tolerance can't be any larger than the MMC. So the MMC of this part is 1.04. You can't add the straightness to that to say, oh, it's 1.05, right? It's still got to be under the MMC, and then you have to achieve that straightness tolerance. Now, there are applications where you could get away with this corrugated roof thing. If you needed it to be straight in both directions, right, you would just use a flatness tolerance, which we'll talk about in a little bit. So straightness controls the straightness in one direction only, and it's usually indicated on a drawing like so. On a 3D model, it's got to be shown with an arrow or something. It's got to be more clear. And an orthographic projection, it's pretty straightforward. Next up, it can apply to a cylindrical feature. So this is applying to the surface elements of a cylinder. This is pretty straightforward to check. You just put it in a V block and run an indicator across. Same thing here. You could just run an indicator across and look at the indicator reading. It applies all the way around the cylinder, but only individual line elements. So you can check one, spin it, check again. You could even shim the part to a degree and check. You only care that the individual line elements are straight. There's no relationship to any of the other line elements on the part. And again, it only applies in this direction, not in this direction. So you could end up with a part like this if it uses its full size tolerance in manufacturing, okay? Next up, it can also apply to conical features. And in this case, inspection-wise, you'd put it on a sign bar in a V block and then just run an indicator across to see if each individual line element is, in fact, straight, okay? So now, let's talk about straightness of a derived median line. Okay, if you notice on these, it's leader directed to the surface. It could also be attached to the extension line. Right. Notice there's no datum references, and you notice there's no diameter symbol in the feature control frame. Right? When it applies to a derived median line, we're going to write it differently. So let me show you what I mean. So there's a couple key differences in this situation. If you notice, the feature control frame is now attached to the dimension. That's a dead giveaway that applies to the feature of size, not to a surface. Also, we've got a diameter symbol in the feature control frame. This indicates that the tolerance zone is cylindrical. It happens to be in the middle of the part. So this tolerance is telling you that the derived median line of this feature needs to be within a 10 thousandths diameter tolerance zone in the middle of the part. Okay? Very different from surface straightness, and it's written differently. Okay? Another thing, because it's applying to a feature of size, now material condition applies. So this applies at RFS. You have 10 thousandths of tolerance no matter what size the feature comes in at. But if we put an MMC symbol here, now that tolerance only applies when the feature comes in at its MMC, in this case 1.04. If the feature comes in at 1.00, we'd have 50 thousandths straightness tolerance, okay? So the part can be more bent the smaller it gets. One thing to notice here is whenever you apply a straightness tolerance to a derived median line, you're giving it more tolerance than you would if you just used plus or minus dimensions. So what it's doing is violating the MMC boundary. If you think about it, if you have a 10 thousandths tolerance zone going through the part right here, so the part comes in at MMC and it can bend 10 thousandths, that means it can take up more than its MMC. It can take up 1.06, right? So it violates MMC. I have a whole nother video that I go into a little bit more detail about this, and I'll put a card up here so you can watch that if you're interested in the difference between a derived median line and an axis. We'll just go ahead and move on for now for this video. The next tolerance we need to look at is flatness. Flatness is extremely common on drawings because a lot of parts are rectangular, and when you use GD&T, you establish datums. Often they're datum planes. Flatness is used to qualify those datums. So if you've seen my other videos, I've said that datums are places to measure from. You want to make sure your datums are good, clear features, right? They don't need giant form variations that can make measuring difficult. So flatness is often applied to datum features so that you have a good place to measure from. So let's look at flatness. Just like straightness, applies in two very different ways. It can apply to the surface of a plane, or it can apply to a derived median plane. Luckily, it works a lot like straightness. Let me give you an example. So I got two examples on the board of flatness tolerances that are applied in different ways. So just like straightness, if flatness is applied with a leader to a surface, it only applies to that surface. So the surface must lie between two parallel planes that are this distance apart. No datum reference, it's an individual feature, so those parallel planes can move around relative to the rest of the part. This is normally checked with the indicator running across the surface, either flipping the part upside down or right side up. Now, I have a whole nother video about that. I'll try to put another card up here. Now, just like straightness, if the flatness is applied to the actual dimension, it means something different. It means it applies to the derived median plane, which just means you have two parallel planes going through the part that the derived median plane of the part should lie in. So what that looks like in practice, if we take an imperfect part and we measure each 2 points on the outside through the whole length and depth of the part. Remember, it's a 3D thing. We're just going to find the middle of each of these points, right? So kind of finding the median of the surfaces of the part, the opposing surfaces. Those points must lie with these 2 parallel planes in the middle of the part. Now, flatness of derived median plane, I would say, isn't used that often. If it is used, it'll typically have the MMC modifier. It's a quick way to check like little sheet metal parts, right? You could just drop it in a gauge and make sure it hasn't violated. So in this case, you would check a part with a gauge that's 1.06. As long as it fits through the gauge, you know the flatness tolerance is good, and you just use a 2-point check to make sure it's not under size. Okay. Let's move on to circularity tolerances. So in my opinion, circularity is not used as often as flatness or straightness, but it's still out there. So what circularity does is control the circularity, right? So whether a cross-section of a circular feature is circular or not. So what do I mean? Circularity tolerance will be applied with a leader line to the surface, and this is the only way it should be applied. Previous versions of the standard, you could put it with the dimension, but that gets confusing because the circularity does not apply to a feature of size. It applies to the surface of the cylinder. So it's saying that at every cross section, right? So say we take a slice right here, we've got two concentric rings, that's tolerance zone, this distance apart radially. So from here to here. And the surface of the part has to lie within those 2 concentric rings at every cross section. Now, the cross sections should be perpendicular to the axis of the feature, okay? So this cross section should be perpendicular to this. But similar to other form tolerances, it only applies to these individual there's no requirement for the length of the part to be straight, just that each individual section is circular. So you could end up with a part that looks like this, right? The length of the part can use the entire size tolerance. So this whole 80 thousandths, so the difference between the high and the low points can be 40 thousandths. So the surface can use the entire tolerance here in this direction, but as long as each cross section is circular, the part is considered good to go, okay? So separate checks, a typical way to check this, you put it in a V block, put an indicator on it, and rotate it around. Now again, no datum reference, so there's no other features you're checking this to. You're just checking it to itself. Now, you might wonder, how could this possibly be acceptable? Well, normally the size tolerance will be pretty small if a circularity is applied. Now, if you wanted to control the straightness of this surface, we would use cylindricity. So let's get into that. Cylindricity controls both the circularity of the feature, each cross-section, and the straightness of the whole feature. So cylindricity is a much more difficult tolerance to inspect and produce, but it gives you more what you're thinking of when you apply a circularity to something, and that it controls the entire feature. Cylindricity can be used for cylinders that are primary datum, so you want to make sure your datum surface is nice and straight and circular. It's often used for things like hydraulic cylinders that have really exacting tolerances and need to be perfectly straight and circular to function correctly. And cylindricity only applies to cylinders, whereas circularity can be applied to a conical shape, a sphere, or a cylindrical shape. So that's it for a quick discussion of the 4 form tolerances. If you enjoyed the video, please like and subscribe, and check out the channel for more GD&T videos coming soon. In this video, I'm going to cover orientation tolerances. So there's 3 orientation tolerances: parallelism, perpendicularity, and angularity. They all control angular relationships. So there's 3 really important things that they all have in common. The first is that they require datum references. And this is logical. It's not something you need to memorize, right? If you're going to measure how parallel a tabletop is to the floor, right? The floor is your datum. You have to have somewhere to measure from. Think about a flagpole. If you want to know how perpendicular a flagpole is, you have to reference it to something. Normally, that will be the ground, right? So all orientation tolerances require a datum reference. It's just a place to measure from. Now, the next thing is that orientation tolerances do not control the location of features. Now, this is a little bit more difficult, but think about it this way. So you're going to go measure your tabletop to see if it's parallel to the floor. So you grab a tape measure, you measure a couple points on the top of the table, and you find out the top of the table is 30 inches, 30 and 1/8, 29 and 7/8. So the top of the table, you could say, is parallel within 1/4 inch. That's the difference between your highest measurement and your lowest measurement. Now, if you measured another table that was taller, and you got 50 inches and 1/8, 50 inches, and then 49 and 7/8, right? The parallelism is still 1/4 inch. Thus, the location, the distance from the top of the table to the floor doesn't matter when you're considering parallelism. So all of the orientation tolerances work within some other tolerance. A lot of times it's going to be the limits of size. So you're going to have a plus or minus dimension controlling the location, and then an orientation tolerance refining that location. So think about the example with the table, right? Your dining room table, nobody's really going to care if it's a 1/2 inch taller than somebody else's or a 1/2 inch shorter than somebody else's table. But you are going to care if within that 1/2 inch, it's angled, right? So every time you put a Sharpie on there, it's going to roll off. You don't want that. So the location of the top of the table matters less than the parallelism, right? So I'll show you on the board in a second. The parallelism just refines the plus or minus dimension and makes things, cheaper to make. The last thing with orientation tolerances, as far as what they all have in common, is that they can apply to surfaces or features of size. Now, luckily, on the drawing, it is very, very similar to how form tolerances are applied. So if you see orientation tolerance applied with a leader directed to a surface or an extension line, or the feature control frame attached to an extension line, it applies to a surface. If the feature control frame is attached to a dimension with the plus or minus tolerance, then it applies to a feature of size. So they can apply to either an axis or a center plane. So let's dive right into parallelism applied to a surface, and then I'll do perpendicularity applied to a surface, and then we'll talk about application to features of size. So parallelism applied to a feature of size must be done with either the feature control frame pointed with a leader like shown, or you could have the feature control frame attached to an extension line that goes to that surface. Now, the tolerance zone for this is 2 parallel planes, the distance apart being this number right here. Those 2 parallel planes must be parallel to the datum. Okay, so what you got here is, a size dimension, 2 inches plus or minus 40 thousandths. No matter what, the surface has to be within that. But within that, now you have 2 parallel planes 20 thousandths apart that can float within that larger tolerance zone. So this 2.04 is our MMC. No matter what, the surface can't go past the MMC. So this 20 thousandths is not additive to the part. But the surface can be up here or down here as long as it's between these two parallel planes that are 20 thousandths apart, those two parallel planes being parallel to our datum surface. Now, normally you check this on a surface plate, right? You put the part on the surface plate and you get a height indicator and just run it back and forth. And that will tell you whether it's parallel to the surface plate or not. So this is a really common tolerance out there, a parallelism applied to a surface. What it gets you is a parallel surface to here, and you can use a larger size tolerance for, like we were talking about with the kitchen table. Sometimes you don't really care the overall height of something as long as it's parallel to a datum. Usually, sometimes that can achieve your design goals. One other thing, if you notice, there's no material condition modifier in here. It can't apply to something that applies to a surface. So rule number one applies, like what I just mentioned. The actual surface of the part can never exceed the MMC, and no material condition, no MMC or LMC or RFS can apply to this. Another thing I want to mention is that if the surface is between these two parallel planes that are 20 thousandths apart, we can also say that the surface is flat to within whatever the parallelism tolerance is, okay? So the check for flatness is very similar, so you never have to put a flatness tolerance unless it's smaller than this, okay? So sometimes you'll see a parallelism with a flatness, but the flatness needs to be smaller or it wouldn't make sense. So parallelism of a surface automatically controls the flatness up to this value, okay? Now, another concept that applies to parallelism is known as tangent plane. So what tangent plane does is just consider the high points of the part for the parallelism. What this effectively does is release the form requirement, the flatness that we just talked about, from the parallelism. Let me show you what I mean. So the tangent plane symbol goes right behind the tolerance. And what it's saying is that only the high points need to be considered for the parallelism check. So how this can be done is you take a precision block, so if it's a small part, a gauge block or a sine bar, something you know is very flat, set it on the top of the part, and then see if that is parallel to the datum. Okay? So what this allows is you can have more valleys in the part because these points are not being considered for the parallelism. This tolerance probably isn't used all that often, but as far as function goes, when your part mates up to this, as long as the mating part is nice and flat, it's only going to touch the high points anyway. So if you have like rough stock, so something in your storeroom has been pitted by rust or something, it might fail a traditional parallelism check, but it might pass the tangent plane check and still be just as functional. Okay? So let's move on to perpendicularity applied to a surface. It's very, very similar. So in this case, I've applied the orientation tolerance to the extension line. So what it's telling you is it's this surface being controlled. So we're saying that this surface is perpendicular to the datum. Okay? As far as a check on the plate goes, it's about the same, except you typically put this up on an angle plate and get it vertical so you could check it a little bit easier. Now I won't draw the tolerance zones for the perpendicularity because it's the same as parallelism. What I do want to mention is that you can have more than one datum reference. So if you have two datum references with the perpendicularity, it doesn't control location. It just controls rotation when you go to inspect. So let me show you what I mean. So here's a super common setup for a datum reference frame. So we've got datum A, B, and C. The primary datum, and we know it's primary because I've got it in this position as the first datum listed, is controlled with a flatness tolerance. This is usually used just to make sure the place you're measuring from, the datum, is good, right? You don't want it to be a feature with a bunch of variation on it when you're measuring from it. Okay, so we've got the flatness applied to this bottom surface, so this surface right here, and then the datum feature symbol applied to that extension line. Next, we've got datum B, which in this case would be this surface right here, perpendicular to datum A. So when we go to check this, we'll put it probably on an angle plate and then run an indicator across this surface until we get the correct reading, okay? At that point, you can move the part, right, like this to achieve the best reading. Next, datum C is perpendicular to datums A and B. Like I mentioned, this doesn't control location. This just has to do with rotation when you're inspecting it. So what this means is you'll get 3 points of contact with datum A. You're going to push it up against something for datum B, and now the part is locked, except that it can move up and down, right? Remember how I mentioned these tolerances don't control location. So 3 points on datum A, push it up against an angle plate, and then you can move it up and down and then run an indicator across it. You can't move it up and down in between measurements though, right? So you move it here, right? You run your indicator. If your indicator reads less than 10 thousandths, you're good to go. If your indicator is bottoming out or something, you can move the part down, start over, and check it again, okay? So that second datum just controls the rotation as you're inspecting. What all of these do together, if you remember, or if I haven't mentioned it yet, a datum reference frame is 3 mutually perpendicular planes. Now, in theory, it's perfect. In reality, it's not perfect. But what we're trying to do with this is what's known as qualifying the datums. We want to make sure our datums are perpendicular to each other in such a way that we get repeatable measurements. Okay? So let's chat about perpendicularity applied to a feature of size. So in this case, I've got a pin that's pressed into a plate with a perpendicularity applied to it. If you notice, the feature control frame is attached to the dimension. Inside the feature control frame, we've got the diameter symbol that indicates that we have a cylindrical tolerance zone. The axis of that pin should fall within this tolerance zone in reference to datum A. So you can imagine a tolerance zone, 20 thousandths in diameter, shooting straight up from datum A. The axis of the actual feature must lie within that tolerance zone. Now, when this is applied to a feature of size, material conditions do apply. So this is applied at RFS, which just means that that tolerance of 20 thousandths applies no matter what size the actual feature comes in at. Now, if we apply it at MMC, we'll get a very different result. Let's take a look. So if we make a chart where we compare the size of the actual feature to the geometric tolerance, we're going to find out that if the feature departs from MMC toward LMC, so the pin comes in smaller, we get more geometric tolerance equal to that difference. So if the pin comes in at 1 inch instead of its MMC of 1.02, we get an additional 20 thousandths of perpendicularity tolerance. That means that cylinder that the axis of the feature must fall within now gets bigger. And now the cylinder is a 40 thousandths diameter. If the feature comes in at LMC, we get 60 thousandths of geometric tolerance. It means the pin can be more crooked. If we add the size to the geometric tolerance, we get the virtual condition. So the virtual condition represents the worst case mating envelope. So what it does is takes into account the size and the orientation to see how much room that pin could take up in reference to datum A. So if you get a mating part that is set to the virtual condition of this, 1.04 or larger, the mating part will fit over the pin and make full contact with datum A. This is really important for design and inspection. So we can check this part with a gauge because we can verify this with a fixed gauge and we can verify the size with a 2-point measurement. This saves a lot of money if you can afford it and your tolerance stack up. Now, the downside is that these aren't great for locating features. Now this is perpendicularity, not position, but as the pen gets smaller, you get more variation in your stack up. Now, what happens if we set the geometric tolerance to 0, right? And we can do this. Check it out. If we set our perpendicularity tolerance to 0, what it means is you have 0 perpendicularity if the feature comes in at MMC. It's got to be perfect. But if the feature comes in small, you get that geometric tolerance back, right? Up to the total size tolerance. So this is plus or minus 20 thousandths. That's the total amount of perpendicularity tolerance you could have if the feature comes in at LMC. You also get a virtual condition with this, which is going to be a little bit smaller, right? So 1.02 for this feature. That would be the diameter, the smallest diameter of a mating part that would fit over the pin and make full contact with datum A. Now, if you had a mating part that was smaller than the virtual condition, okay, say you had a mating part that was 0.98, it might fit over the pin, but it might not make full contact with the datum, right? You imagine, this pin is crooked and you try to fit something on there, it's gonna touch one portion of this, not the whole thing. The next thing I want to talk about is the concept of an actual mating envelope. So if you're wondering, how do we find out where the axis of this feature actually is, the way we do it is with the actual mating envelope. So the actual mating envelope is a similar, perfect feature counterpart of smallest size that can be contracted onto an external feature, or of largest size that can be expanded on an internal feature. Now, that sounds really complicated, but it's really not. So let me show you on the board. So I've got a pin, and then I've got a hole, okay? They both came in with a lot of variation. If we wanted to know what the actual mating envelope of the pin is, we would collapse a cylinder on it. So think about if you put a drill chuck on this and you're collapsing the drill chuck until it makes maximum contact. You would end up with a cylinder that collapses on that part, and the axis of that perfect cylinder becomes the axis of this feature, right? That would be the axis we would use to figure out if the perpendicularity tolerance is within tolerance. Now, as a practical method, this can be simulated with a collet or a ring gauge or all kinds of things, or even just running an indicator over it. Now, for an internal feature, a hole, this is usually simulated with gauge pins, right? So you find gauge pins and you put one in, and if it fits through, you go to the next size up, see if it fits, and you get the largest gauge pin that will fit in the hole, and that's going to simulate the axis of that actual feature. So the largest gauge pin that would fit in that feature is going to touch the high points, and the axis of that gauge pin is the axis of that feature. That's what we would use to figure out if it's within tolerance for perpendicularity or even things like position, okay? So this is great because it's really functional, right? Because normally we care about the high points, not the average of all the points. The next thing, this is unrelated actual mating envelope. It's what we use for position and perpendicularity, but there's another concept known as the related actual mating envelope. The difference is
the related actual mating envelope is constrained to datums. So let me show you an example. If we wanted to know the related actual mating envelope of this pin pressed through this plate in relation to datum A, we're going to collapse the cylinder onto the pin. Okay? But that cylinder has to make full contact with datum A as well. So if we just slid a ring gauge over this, right, the axis of the ring gauge would be about right there. But that's not what we're doing. This would be the unrelated actual mating envelope. The related actual mating envelope needs to stay in contact with datum A. So imagine you got a cylinder sitting on datum A and it's collapsing. Eventually, it's going to touch one point of the pin here and one point of the pin here. Now, that opening is going to be larger than if you just collapsed it on the pin, because now it's taking into account a datum. This is the related actual mating envelope, which also is usually the virtual condition. Okay, so the concepts kind of work together. The next thing I want to chat about is parallelism applied to a feature of size. This is only for axes, and where you'll see it is if you have two cylinders, so something like a connecting rod for an engine, where you have a basic dimension between them. You'll have a position tolerance on one of them, and then a parallelism refining that position tolerance. It's not super common because you can just use a composite position to achieve the exact same thing. Another thing I want to mention, you can use parallelism tolerance with a profile, but a profile tolerance does the same thing as well. Okay, so there's certain areas where you could use an orientation, but a position or a profile essentially does the exact same thing. Okay? So the orientation tolerance we did not talk about is angularity. Angularity is used for angles that are not 0 or 90 degrees, but confusingly, you could use angularity in the place of parallelism or perpendicularity. That's a newer thing in the ASME standard. The way you know the difference is just looking at the lines on the drawing. So if the lines are drawn as perpendicularity and then it's not stated anywhere that it's not 90 degrees, you assume it's 90 degrees. Same thing with lines that are drawn parallel. This is fundamental rule J from the ASME standard. Now, whereas you can use angularity in the place of parallelism and perpendicularity, I wouldn't recommend it because it's going to confuse people, but it's possible. So angularity does the exact same thing as all that stuff I've been talking about. You can use it on a surface or a feature of size. It's not quite as common as the other ones. For a surface, you'd probably use profile instead. It would accomplish about the same thing. For a feature of size, it's possible, but again, you'd probably just use position or composite position to achieve the same thing. So that's it for this video. Didn't cover every possible permutation of orientation tolerances, but these are the highlights. This is the stuff you need to know. I hope you found it helpful. If you enjoyed it, please leave a comment down below, like and subscribe. In this video, I'm going to discuss datums. So in the ASME standard, this section is number 7, and it's called datum reference frame, not how to use datums. The reason is that the datum reference frame is really important to understand. It also is fairly simple. It's really just another word for Cartesian coordinate system. So in the Cartesian coordinate system, you have X, Y, and Z. They're normally represented by lines going in totally opposite directions. They're 180 degrees from each other. They're 90 degrees from each other. Now, in GD&T, our datum reference frame is represented by 3 mutually perpendicular planes. Now, theoretically, they're perfect. They're exactly 90 degrees apart. In reality, they're not. And we'll at some point talk about how we square the circle with that, theoretical and what you can actually inspect. Now, our datum reference frame looks like so. We have one direction in X, another direction in Y, another direction in Z. This is our 3 dimensions, and it's what we usually need to measure parts. If parts are really, really thin, like sheet metal, sometimes you only need to worry about 2 dimensions, the X and the Y. Now, there's another concept called degrees of freedom. This is really important for inspection. It is the order in which you constrain the feature so that the feature doesn't move around on you while you're inspecting. Let me show you how it works. So I've got this part drawn on the board. We've identified this bottom surface as datum A, this surface is datum B, and this surface is datum C. We want to set the part up for inspection, right? You can't just guess. You can't just put it down and measure from wherever. The instructions are given right here. These are our datum references, and this is the order of precedence. So it's saying make maximum contact with A, and then B, and then C. And those, when we do it in that order, they're going to take away the degrees of freedom in the order the designer intended. So if I take this surface and I put it up against my whiteboard, I've taken away degrees of freedom. Now, which ones? Well, we can move the block around, right? But we want to know where we can't move it. So if it's on the board, it can't move like this, and it cannot move like this, and it can't move in and out anymore. So we've taken away the translational degree of freedom in Z. We've taken away 2 rotational degrees of freedom, both V and U. Now, you almost never have to use the U, V, and W. I put them up here. They're just the rotational degrees of freedom. So we've taken away 3 degrees of freedom with our first datum reference, datum A. Datum B, we're going to, while it's constrained to datum A, constrain it to another surface. If you notice, you can hear it, 1, 2 points of contact. It's got to be a minimum of 2. It can be more than 2. But what we've done, when I'm just pushing it up against the bottom of my board here, we've taken away another degree of freedom. We've taken away Y, because it can't move up and down anymore if it's stuck to the bottom. And then we've taken away a rotational degree of freedom, and then it cannot move like this. Okay? The last is datum C, which is going to be this side right here. And I actually drew my angle plate on the wrong side, so let me draw it again. So we're going to push it up against something. On an open inspection, a lot of times it'll be something like an angle plate. Now, it only needs to make 1 point of contact with the angle plate. The reason being, it's only controlling 1 degree of freedom, just the translation. To stop it from moving left and right, you only need 1 point to achieve that. At this point, we've constrained this part in all 6 degrees of freedom. We have to do that for location and profile that controls location. So in order to measure the location of these holes, the part has to be fully fixtured, right? It can't move. So when we go to measure the holes, all of the measurements are going to come from this bottom corner, right? Because we've got a datum here, got a datum on the angle plate, and we've got the board. Okay, so everything is in reference to that bottom corner. That's the 0, 0, 0 of this part. Now, it doesn't have to be that way. It depends what order the datums are put in here. And it doesn't have to be flat planes. Datums can be features of size. So a datum could be an axis, or it could be a center plane, right? Remember, datum is a theoretical point, line, or plane. So the line could come from a cylinder. The plane could come from 2 real planes to make a datum in the middle of the part. Let me show you what that looks like. Now, I've identified datum B as a center plane. What this is saying is that the center of this part is where the measurements need to come from. So we've moved the origin from one side of the part to the center of the part. This is really common in symmetric features where you don't favor one side or the other. The way this is supposed to be inspected is you have some kind of centering vise that grabs it, and then you can find the 0 and measure out from there. Another thing I want to mention is that when your datum is a feature of size, it does have a material condition, just like any other feature of size. So in this case, datum B is shown here. It applies it regardless of feature size. Datums A and C do not. They're planes. They don't have size. They're not features of size. But datum B could have the MMC modifier. That way, when you go to inspect it, you don't need that expensive centering vise. You could just set two angle plates 2.02 inches away, so the MMC of that feature or the virtual condition if it applies, and then measure from the center of those two angle plates. The part could move around between them. Okay? It's a little bit more complicated to set up, but what it allows you to do is have something like a robot check parts for you, because now you have fixed gauging. You don't have to center the vise and then find the middle. Okay? One thing I want to mention when we do use the MMC, so what it's known as when it's used the datum reference is MMB, maximum material boundary. You can still check it as if it's RFS. That's totally fine. RFS is always a more stringent call out than MMC. So anything that says MMC, you check it as if it's RFS and it passes, you're good. It's only when the piece fails that you might need to go back and account for the MMC or the MMB. The next concept I want to talk about is true geometric counterpart. This is kind of like actual mating envelope, but for datums. So all the true geometric counterpart is a perfect shape that's the opposite of the datum. So if your datum is a flat plane on the part, the datum simulator is a perfect flat plane that touches it. If your datum is an external cylinder, the datum is an internal cylinder that collapses onto that external cylinder. So imagine a collet or a chuck squeezing onto something. That would establish the axis of that cylindrical datum. True geometric counterparts are used or simulated with datum feature simulators. Okay, so just inspection equipment. Or if you're using a CMM, the computer code in the CMM will just figure it out for you. Now I want to talk about some of the ways datums are identified on the drawing. If I didn't go through it before, the terminology with this, a datum is a perfect line, point, or plane. A datum feature is a physical portion of the part. So this plane is our datum feature. Datum feature symbol is this little guy. So the letter in a box with a little triangle pointed to something. It tells you which feature is a datum. The datum reference is in the feature control frame, tells you what order to use your datums and at what material condition the datums apply. And then the datum feature simulator is just your inspection equipment. So a surface plate for a regular surface datum, or a mandrel if you have an internal datum, so an internal hole. You could use a mandrel to expand and capture that. Gauge pins also work. The largest gauge pin is the feature simulator for a lot of holes up to about 1 inch. So let's go into some of the ways datums are shown on drawings. The first example I have here, our datum feature symbol is attached to the extension line, but it's not in line with the dimension. The datum feature symbol could just as easily be attached directly to the part surface. That would do the same thing. It just cannot be in line with the dimension. The reason being is that if you do that, as in this example, it means that the datum is the center plane of this feature, not a surface. So in this example, this surface is the datum. In this example, the datum is in the middle of the part. Inspection-wise, you have to tackle that in a different way. Neither side of the part is more important than the other. Now, I recommend if you're making drawings and you want it to be a surface datum, take your datum feature simulator, take your datum feature symbol and just flip it upside down. That way there's no guesswork involved, right? Often when you're changing drawings, things can kind of just move on you. You don't want a situation where the datum is really close and you're not sure whether the designer meant for it to be a center plane datum or they meant to be a surface datum. Another giveaway is there should be a center line going through this part because it's symmetric if the datum is the center plane of the part. Next up, when it's a datum is a cylinder, so I have two diameters here, one of which has a plus or minus dimension and the datum feature symbol in line with the dimension. That means the axis of this diameter is the datum. You're comparing the axis of any other diameters to that diameter. Okay? Now, you often have feature control frames on your datum features. So I've given a couple examples here. Flatness could have the datum feature symbol attached to the feature control frame. Just indicates that this surface is the datum. Here's a flatness applied to a derived median plane. Okay, so this has a datum symbol attached to it. It means that this is the datum. With a cylindrical feature, we've got a feature control frame. Normally, right here, you wouldn't put the datum feature symbol on the feature control frame because it'd get in the way of the dimension line. So you would do what I did right here, move the dimension totally out of the way and then put the feature control frame on it. Now I want to mention, in the 1994 standard, okay, you were not allowed to put a datum feature symbol on a feature control frame unless it applied to a feature of size. So any drawing made to that standard, if you saw a datum feature symbol on a feature control frame, you could assume it was a feature of size. It's not that way anymore. In 2009 and 2018, you can put the datum feature symbol on any feature control frame. So this applies to a surface. This applies to a feature of size. It's kind of a free-for-all. I personally like the old way a little bit more because it made drawings slightly quicker to read, because if you saw datum feature symbol on a feature control frame, you already knew it was a feature of size without having to do any more looking. But rules change. Now, I want to take a look at a couple other types of datums. The planes and cylinders are the most common. Okay, almost, most parts you can get away with either a surface plane, center plane, or the axis of an internal or external cylinder for a lot of your datums. But it's also somewhat common to see threads called out as datum features. So in this example, we've got a thread and then a diameter that's positioned to the thread. If the thread is what is controlling everything in that part, then it should be the datum if it's the most important thing. In this case, there's a whole lot more length for the thread to grab onto than there is for this diameter, so it makes sense as a datum feature. Now, the tricky part is that when you go to inspect this, unless otherwise specified, the datum is the pitch cylinder, which is an imaginary thing in between the top and the bottoms of the threads. This requires expensive inspection equipment to capture, depending on the thread size, but it is the most functional because that is what's going to locate the thread at assembly. Normally, if a thread is the primary datum, there won't be a feature control frame attached to it, so no straightness or anything. The reason being that threads have their own tolerances already, so you don't need to control the form of a thread, so no need for a straightness tolerance. The datum feature symbol is just attached to the bent portion of the leader. Now, an option for designers is to identify the major diameter for external thread or the minor diameter for internal thread as the datum. So it would look like this. This tells the inspector that they don't need to find the pitch cylinder. They can just take the outside diameter of the thread and use that to simulate the datum. So they could just put the thread in a V block and they're done, right? It's easy enough, preferably a collet or something, but they could treat it just like any other diameter. It's not special in any way, really. The downside, design-wise, is that the major diameter doesn't locate the thread as good as a pitch cylinder, so you wouldn't want to do this if it's really critical to locate something. I mean, you really shouldn't use threads to locate things, but I guess it just depends on the stack up you're looking at. This could induce error at assembly that's difficult to keep track of. Right? So next, you can use profile shapes as a datum. So what I'm talking about are irregular features. So in this case, I've got a slot shape that's an external feature. So it's a, what do you call it? So it's a slot shape with 3 holes going through it. You could pick, this side or this side to favor and make one of those a datum, or you could, tolerance the outside of this with a profile, and I should have a all-around symbol there. Dimension it with basic dimensions. I left that part out, and make that the datum. This is allowed. So that takes away 5 degrees of freedom, right? Because it's a special shape. It can't move in any direction except up and down. So datum B is one of the top or the bottom of this part that locks down the last degree of translation. You probably wouldn't want to specify this as RMB or RFS though. The reason being, what you're telling the inspector, if you do this as a primary datum, in order to have a true geometric counterpart at RMB, you'd have to have a perfect opposite shape, so an internal slot that collapses at the same time to catch the high points. That kind of stuff is possible to produce for inspection, but generally, unless you have a really good reason not to, you want to specify that at MMC or MMB so that they could, make a slot shape, drop it in there, and then check the position as normal. Okay, so basically the part can rattle around a little bit. I have another video about that. I'll put a title card up. Now, you can also do this with like a cone shape if you apply a profile to it, and that would lock down even more degrees of freedom. But using these as primary datums, I would warn against it unless you have a really good reason, or if your company has CMM machines that can just figure it out for you. This kind of stuff could be very difficult to inspect on open inspection with height gauges and whatnot. So next up is using a pattern of features as a datum. This is common, and it's a good way to establish that the pattern is important and then everything around it is less important. So here we've got 4 holes that are positioned to datum A. We have to use position because they're a pattern. Perpendicularity wouldn't have anything to say about how far the holes are from each other. We need to use position for this application. So position, diameter 30 thousandths MMC to datum A, but this pattern establishes datum B. And then all of the other features of the part are going to be relative to the pattern. Now the tricky thing with the pattern is that none of the holes individually is the origin for measurements. The origin is actually in the middle of the part, right? So that pattern creates an axis in the middle of the part, or you could think of it as 2 planes in the middle of the part. you essentially are going to measure from the center of those 4 holes. Again, on a CMM, this is super easy. On a plate, you basically have to have this set at MMC. The reason, when we look at this center hole, right, we're going to position it to datum A and that pattern of holes. If you called that out at RMB or RFS, you would have to have 4 pins that expand at the exact same time, that are perfectly located, so at least gauge maker's tolerances. They all expand to capture the part until it stops wiggling. That can be done, and they do make fixtures and gauges for that. But if at all possible, if you can use the MMC modifier, it's possible that you could have fixed gauging for that. So you could have a robot drop the plate on 4 pins. If it fits, it can check the next thing, you're good to go. At worst case, you could check it with the CMM machine, and then the MMC just gives you extra datum shift if you need it. So this outside right here has a profile to the same datums, A, B, and MMC. This is great if the outside of the part mates to air, which just means that there's nothing it's going to touch at assembly. So you could think of the outside of a television screen mates to air. A lot of things mate to air, and you want to be sure to give that kind of stuff as much tolerance as possible because it's not functionally very important. The last thing I want to talk about are multiple datum reference frames. So the example I give here, we've got 2 holes in a long bar. So let's say this bar is 5 feet long, okay? So we're going to measure the location of the holes. If we use a traditional dimensioning scheme, we've got A as the large surface here, we've got B as the long side, and C as one of the ends. So we go set up to inspect, no big deal for this hole. For the one that's 5 feet away, so we're measuring from datum C to find this location, we're going to have difficulty getting inspection equipment that is accurate enough that can span that far. Also, it depends on the function, right? If this hole does something over here and this hole does something over here and they don't really work together, we can separate them tolerancing-wise. So what we're going to do, instead of both of them using the same ABC datum reference frame, as we talked about before, the ABC is how you set it up for inspection. A first, B second, C third. All your measurements would come from this corner right here. Let's add another datum. So we're going to add datum D, which we're going to establish as this side of the part. We need to have a tolerance for that datum because we're using basic dimensions. We need a profile to establish the location of that surface from this side. So that profile is going to be to A, B, and C. So we're still going to have to measure that to make sure that's within tolerance. That comes and makes datum D. Now this hole can be measured from A, B, D from this side. So inspection-wise, it can be a little bit easier depending how you set it up. Functionally, this could help as well. If this hole is just sliding over something that has to do with one edge, it would be the same over here. You're measuring from the edge of the important side, not the total other side of the part. Okay? Whenever you do this, though, you're going to introduce extra tolerance stack up whenever you have multiple datum reference frames. It also causes inspectors to have to set up differently, right? So this is a different datum reference frame than this. It requires a different inspection setup to make that happen. If you're programming a CMM, probably a little bit easier, but you still have to remember to punch in the right stuff. So that's it for this first talk about datums. I'll probably do another longer video about this soon. Datums is a huge topic. There's a lot to cover. I think this is good enough to get everybody started. So if you enjoyed the video, please like and subscribe. Leave a comment down below. In this video, I'm going to go over runout tolerances. So there's two runout tolerances, circular runout and total runout. What they do is control the surface variation relative to a datum axis. It's convenient to think of them in terms of their counterpart form tolerances. So circular runout is very similar to circularity. The difference being circularity is a form tolerance, so there's no datums. You're just seeing if each individual cross-section is circular. Whereas circular runout, you're checking the circularity, but to a datum. So you're gaining the location of that circle to your datum axis. It's the same thing with total runout. In total runout, you're checking the cylindricity to a datum axis. So you get cylindricity and you get the location of that cylinder to your datum axis. So runout tolerances have a couple of common attributes. They always require at least one datum axis because the inspection is to rotate the part 360 degrees and then see what the surface variation is. So it would look something like this. Right. You grab your part, you put it in a precision collet, chuck, V-block, whatever, so that you can spin it 360 degrees and the part stays true to the datum axis. You put an indicator on it and then you see what the indicator reads. Runout can use two cylinders or two conical surfaces for a datum axis. Now I'll show you an example in a minute, but when you use two diameters for one datum, you only get a single axis. So if I have this part and this cylinder are defined as datums, and it says you use them both at the same time, it's intended that you grab both of them. When you spin the part, there's still only going to be one axis of rotation, okay? So that, even though there's two datums in the feature control frame with a hyphen, still only one datum axis. And then surfaces perpendicular to the axis of rotation can be controlled with a runout. So I'll put the first example on the board. Here we have two diameters with a circular runout of 10 thousandths applied with a leader to the smaller diameter. If you notice, the runout tolerance is smaller than the size tolerance. This is the most common way to do it. So in this example, the runout tolerance is controlling the form of that diameter, so essentially the circularity, and the location to axis datum A. Now in runout tolerances, the datum references are always at RFS, regardless of feature size. So you have to make full contact with the datum with whatever inspection equipment you're using. So if you have a chuck, you're supposed to collapse onto the part until it doesn't wiggle around anymore, and then you can rotate it 360 degrees. You cannot use any fixed gauging for runout tolerances. Now on this part, the size is not controlled with the runout, right? The size can vary more than the runout tolerance. So, you can still check it with calipers, your 2-point checks to make sure the size is within tolerance, and then everything else would be controlled with that runout tolerance. Now, the difference between circular and total runout is that circular runout is individual checks at every cross section. So if we get our part in a V-block or a collet, we spin it 360 degrees, right, with the indicator on it, we can move the indicator away, bring it back, and spin it 360 degrees. So essentially the indicator can move up and down relative to the axis of rotation. Not while the test is occurring, right? You have to do the full 360 degrees, make sure it's within tolerance on the indicator, and then you could move it up or down for the next check. So what that could give you what that could give you is that if you check it here, right, or here, you could get something that's within the runout tolerance, so relatively circular and located to the datum axis. But along the length of the part, it could vary within the size tolerance, right? So you check here, it's circular and located. You can move the indicator down to check here, right? You can move the indicator down, you can move it up. So circularity does not control the straightness or the taper of a cylindrical feature like this. In this case, the limits of size would control the taper or cylindricity of that particular feature. Now, I've tried to draw the jaws of a chuck here. When you clamp onto the datum feature, the axis of your inspection equipment, so in this case, a chuck, is the axis of your feature, right? So whatever the axis of this is, projects through here, that's what you're spinning about, okay? So it's important to realize you're not spinning about the feature you're measuring, you're spinning about the actual datum. So in theory, that should be the most important feature where it mates up at assembly. Now, because circular runout can be, the checks are individual, it's not limited to cylindrical surfaces like this. It can be used on spherical or conical surfaces as well. So I'll put an image up on the board. So up here is a conical surface. The idea with this, the only difference is that your indicator needs to be normal to the surface you're checking. So if your conical surface is like this, your indicator needs to be normal to this, not normal to the axis of revolution, okay? So perpendicular to the surface. That is the check you're performing. Runout, circular runout could be applied to a spherical surface, which I'll show right here. This check is a little tricky to find out where you're perpendicular to the spherical surface. You're basically normal to it at any given point. So theoretically, you should always be moving your indicator as you're making individual checks, right? So next up is circular runout applied to a surface perpendicular to the datum axis. What this controls is the wobble of the surface. It just makes sure it kind of spins true. It doesn't control flatness. Flatness is controlled within the limits of size because you're doing individual checks. So you could get kind of a waffle-shaped area on a perpendicular surface. Now we'll move on to total runout. Total runout has two arrows to distinguish it from circular runout. Total runout is a complete, what the ASME standard calls a composite control. It controls cylindricity, straightness, taper, profile, everything except the size. So this is only applicable to cylindrical features or flat surfaces perpendicular to the axis of revolution. Not tapers, not cones, not spherical surfaces. The check for this is much more difficult because in order to make sure it's straight along the length, you can't move your indicator. The indicator needs to move parallel and the same distance from the axis of revolution. So that means is that if we lock our indicator in here, spin it 360 degrees, when we check the next spot, the indicator cannot move away from or toward the datum axis. It has to stay locked. It can only move in translation parallel to the datum axis. This is how we control the straightness and cylindricity of that feature. So it's a much more difficult tolerance to inspect and potentially to make. What it does for a flat surface perpendicular to the datum axis, say we're checking this flat surface, it controls the flatness and perpendicularity to the datum axis. Next up, I'll put the image on the board here, is a compound or a multiple datum feature. ASME keeps giving it different names. Essentially, like I talked about before, it's when you have two diameters that form a single axis. So if you know your part is mating between two bearings, right, you want to inspect it as such. So the idea is you grab it with two V-blocks or collets, however you're going to do it, and when you spin it, it'll be spinning on a single axis. Right? Neither datum is more important than the other. They could both be different sizes or the same size. This is often used with very long parts that you couldn't easily control with one datum. This can also be used with machining centers. So occasionally machining centers are called out as datums. They're not the best datum though, because normally machining centers are not very functional. They're just there to aid in making the actual part. So as a designer, I'd only choose a machining center as a datum if there's no other reasonable choice. Whenever you're choosing datums for runout, you want a nice large diameter with a good bit of surface area because the inspector is gonna have to grab it in some way. So if I chose just this small diameter as a datum here, it's gonna be very difficult to capture that with any normal inspection equipment. So at inspection, if it's off, half a thousandths here, and I go to inspect the runout, it's gonna be more off over here. So this would be a prime candidate to make both these datums a compound datum feature, right? So you check it like this, it makes the part more stable. Now, what you'll see on drawings occasionally where you have two datums, but it's not a compound or multiple datum, right? You've got datum A primary, B secondary. So the idea is you would grab the part here, and then you'd have to make one point of contact on datum B. In my opinion, this is superfluous because when you're doing a runout check, translation doesn't matter at all, okay? So in this case, datum B really isn't, very necessary. But in the other case, if we made the surface perpendicular to the datum axis, datum B, then we do need datum A. There always has to be a datum axis for runout because we've got to rotate the part. So in this case, we make full contact with datum B, say against the nose of our chuck or collet or V-block, and then clamp down on A, and then we could spin the part around. So you can have a situation where you make full contact with B, and then A only grabs on one point. And that would be okay in this situation. You're saying B is more important than A. B would be the mating surface at assembly. The next thing is the advantage to runout. Like, why would you use runout instead of position or profile or something? Runout is good for parts that spin because you're controlling the form, the balance of the part. The difference between runout and concentricity is that runout also controls form, whereas concentricity doesn't necessarily control form. Runout covers your circularity or cylindricity, so it's really good for things like pulleys, drive shafts, anything that's spinning and potentially has to mate up at assembly. The outer boundary for a runout tolerance is the largest size, the MMC, plus the geometric tolerance for an external feature. The inner boundary is, in this case, the LMC minus the geometric tolerance. So if you're doing a tolerance stack up, it's pretty straightforward to figure out what your boundaries are. There's no bonus tolerance with runout tolerances, so I wouldn't apply it to anything with like a clearance application. But anything that spins, especially at high speed, runout is a good tolerance to apply. Now the last thing you'll see on older drawings would be called full indicator movement, FIM, or total indicator reading, TIR. So they might point to a diameter and say total indicator reading, 5 thousandths. The important thing with GD&T is that you're specifying which diameter is the datum. If you have several diameters, think about like a stepped pulley, it matters which one you grab to inspect the rest of the diameters, okay? So that's it for this video. Hope you enjoyed it.
Please like and subscribe, leave a comment down below. In this video, I'm going to discuss tolerances of profile. Now there's two geometric characteristic symbols associated with profile: profile of a surface and profile of a line. Profile of a surface looks like a D that's been knocked over. Profile of a line looks like a rainbow. Now the difference between them is that profile of a surface is a 3D tolerance. What that means is it controls an entire surface, whereas profile of a line only controls individual cross sections. So a good way to compare this to something we've already covered is the difference between flatness and straightness. If you recall, when you apply flatness to a surface, it controls that entire surface. You have to run your indicator left and right along the surface. With straightness, if you applied it to a flat surface, you only have to run your indicator in one direction, an individual check. So you could essentially have a corrugated part in the other direction. Profile works in a similar way. The big difference, and I'll explain more about this in a minute, is that profile is not limited to flat surfaces like flatness and things like parallelism are. Profile can be used for curved surfaces, surfaces of revolutions, and flat surfaces. So it's a very versatile geometric characteristic. Now, another thing with profile, which I'll talk about in detail in a minute, is that it can do a lot of different things. Now, profile can mean the exact same thing as flatness if it doesn't have any datum references. Profile can mean the same thing as parallelism or perpendicularity if it only has one or sometimes two datum references. Profile can control the location and size of features if it controls a feature in all 6 degrees of freedom, which normally means 3 datum references. And I'll try to give you some concrete examples of what I mean in just a minute. First, we need to talk about the profile tolerance zone. It's going to be based on the true profile. The true profile is normally dimensioned with basic dimensions. The newest version of the ASME standard, that's the only way you can do it. Older versions of the ASME standard, you can sometimes use plus or minus dimensions with profile, but that would kind of get confusing. Normally, if you've got a profile, you want it to be a basic dimension. The true profile is the theoretically exact place where the tolerance zone lies. So normally, if it's bilateral equal tolerance zone, you got half your profile tolerance on one side of the true profile and half on the other. So imagine this part is defined with basic dimensions. So each of these humps would have a radius on it, which would be basic. You'd have probably the width would be basic and the height would be basic. However it got dimensioned, doesn't really matter for our purposes. Basic dimensions. The true profile is located by those basic dimensions. And when it's an equal bilateral tolerance, aka the tolerance is split on the true profile, which is the default requirement, you've got half your profile inside and outside of the true profile. What I'm trying to get to is that the true profile is normally just the part outline, so the visible lines on the drawing. And then your tolerance zone just follows the part. So the technical way to define it is that tolerance zone is perpendicular to the true profile at every point. So that just means if we choose this point right here, we draw a line through it, it's perpendicular, right? We could do the same thing here, same thing here. It's much easier down here. Right? The length of each of these lines is 20 thousandths. 10 thousandths of the line is on the inside, 10 thousandths on the outside. And then we can just draw our tolerance zone around the true profile or part outline. Now, if you don't stick around for the rest of the video, just know that if you have a unilateral or an unequal bilateral tolerance, this isn't quite true because your tolerance zone can get shifted one way or the other, and I'll go through that in just a second. Now,
What profile is saying is that the surface of the part must lie between these two tolerance zones. Pretty straightforward, right? For a flat surface, it's a fairly straightforward check. You know, you would check this the same as flatness. Now, up here with this curved surface, that's where you can get into problems. That's where a CMM machine comes in real handy, but there are ways to do it on the plate. Now, a lot of the ways are comparative, so you'd have a control part that you knew was just about perfect. You could set your indicator on the control part and then come over to your regular part and check it at individual points. Now, a bunch of different ways to do it, but what I'm trying to get across in this video are the drawing requirements. Now, if you notice, there's no datum references on here because I haven't called out any datums on the part. This would just control the form of the surface and the size of the part because there'd be basic dimensions on here. Now, let's chat a little bit about the limits of application. So a profile tolerance, according to ASME standard, is supposed to apply until there's an abrupt change in direction. That means different things to different people. So one person might say, this is an abrupt change, so this profile goes all the way down here. Another person might say, this isn't an abrupt change, it just depends. The best way to specify it on a drawing, if it's unclear, aka not a sharp corner, is to use the in-between symbol. So we identify the point we want to go to with a note and a letter, and then the other side, the point we want to go to with a note and a letter, or a leader and a letter, however you want to word it. And then under the feature control frame, we use the between symbol, which is just two arrows, and we put those two letters. So we're saying this 20 thousandths profile applies from G all the way over here to H. And then this 10 thousandths would apply on this bottom surface only. You saw me do it before. You can also use the all around symbol if you want the profile to just go around the whole part. What can happen, especially as drawings start to get revised and changed, is it can get a little confusing as to which tolerance applies where. So if you just glanced at this drawing and see this profile 10 thousandths all around, it's possible you could ignore this, even though it's going to take precedence over this. The way you avoid that is beneath this one, we're going to write except as noted to alert the reader of the drawing that there's going to be some exception to this all around symbol. So that just covers us and makes sure the reader is redirected to the other tolerance. Now this isn't limited to profile, this can be used with other tolerances as well whenever you have potentially overlapping tolerance zones, which often happens if you're using the all-around symbol. Now, the all-around symbol is two-dimensional, right? It's just controlling around. If we wanted to apply the same tolerance to the front and the back of the part, we just add a concentric circle, and that gives us an all-over tolerance. So that's a new one that came in the 2009 standard. So you can apply a profile to the entire surface of the part, which can be convenient. Now, let's get into the tolerance zone boundaries. Now, you can have a uniform tolerance, which is the most common way to do it, or a non-uniform tolerance. So you could potentially have the tolerance be wide at one side of the part and narrow at the other side of the part. Now, I'm just going to talk about uniform tolerance boundaries. I think the non-uniform is a more advanced topic. If anybody needs more information about it, I'd be glad to make a video, but for now we'll focus on the nuts and bolts of profile. So the default requirement is a bilateral equal tolerance zone. Like I mentioned before, with this 20 thousandths, you got 10 thousandths on one side and 10 thousandths on the other of the true profile as defined by the basic dimensions. That's not always what the designer wants. So often you would have two mating parts where the basic size is 1 inch. So instead of changing the nominals to make them fit, you could just say, okay, I'm cool with the line-to-line fit. I'll make one unilateral in one direction, the other unilateral in the other, and they're going to fit up no problem. The way that we do that The way we make a profile tolerance either unilateral or bilateral unequal is by using the unequally disposed symbol, which is a U with a circle around it that goes to the right of the tolerance value. On the other side of the unequally disposed symbol is going to be a value, anywhere between 0 and the full tolerance value. So in this case, it could be 0, 10 thousandths, 20, 30, or 40, or it could be a decimal of those, but normally you wouldn't add more decimal places than is already right here. Now, this value indicates how much of the tolerance is in the direction that would add material. Now, what that means, I've got an example here. Now, just imagine this is all defined with basic dimensions. Profile, 40 thousandths, unequally disposed tolerance. 0 of that 40 thousandths is in the direction that would add material. 0 of 40 thousandths is in the direction that would add material. What would add material to a hole? Making the hole smaller. That's saying 0 is in that direction. So the entire 40 thousandths tolerance zone is inside of the true profile is indicated by basic dimensions. In this case, the hole could only get bigger. Now, from a manufacturing standpoint, you probably want to take this and then fix the basic dimension to make it in the middle of here for your tool paths, but that's a different thing. Now, in this case, for the external feature, profile, 40 thousandths, unequally disposed, 0 of that 40 thousandths is in the direction that would add material. What would add material to this square? Making the square bigger. 0 of the tolerance is in that direction, therefore the tolerance zone is totally within the true profile. So that square can only get smaller. Now what happens if we go entirely in the other direction? Profile, 40 thousandths, unequally disposed. 40 thousandths is in the direction that would add material. In this case, the tolerance zone is totally within the true profile as defined by basic dimensions which I've omitted on this figure to save some room. Same thing out here. 40 thousandths, unequally disposed, 40 thousandths is in the direction that would add material. The tolerance zone is entirely outside of the true profile as defined by basic dimensions. Now, let's get into the levels of control with profile. It depends on the datum references. It's a great way to learn GD&T because you have to pay attention to what the datum references are telling you. It gives you the level of control the profile is intended to cover. All right, so the first one, we've got a profile, 10 thousandths applied to a flat surface with a size dimension locating it. In this instance, profile does the same thing flatness does. If you recall, a flatness tolerance is two parallel planes in which the surface of the part must lie between. The profile tolerance zone is worded different, okay? It's perpendicular to the true profile at every point, but what you end up with in either case is a zone of 10 thousandths in which the surface of the part must lie. Now, this zone must lie within this larger limits of size, so this profile does not control location. The limits of size control location. Now, it would be incorrect to use a basic dimension with this because there's no datum right here. So that's using profile as flatness. The next one, we're going to use a profile of 10 thousandths to datum A. Now, what's important here is that we have a plus or minus dimension. Now, this isn't allowed per the current ASME standard. I'm putting it here to just show you how profile works. It's something you might run into. Not everybody makes every drawing per the current standard, right? So what this does, we've got a 10 thousandths tolerance zone to A. So that's essentially a parallelism call out. That tolerance zone needs to be parallel to A, but it's located with this larger plus or minus dimension. So this is essentially profile masquerading as a parallelism tolerance. Again, you really shouldn't do this. You should use a basic dimension, but when we do the right thing and use a basic dimension, if you notice, all of this tolerance went away. Now, the profile is controlling the location of that surface, as well as the size, as well as the form, and the parallelism. It makes it much more restrictive. Even though all we did was change from a plus or minus to a basic dimension, this becomes a much more restrictive tolerance. Now, we can fix that with a composite profile. We could essentially have a composite to 40 thousandths in the top segment and then do 10 thousandths just to A and essentially get the same thing as a plus or minus tolerance. I'll go over that in some other video. Now, profile also does something that none of the other tolerances do. It controls coplanarity. Now, in the ASME standard, it's clearly stated that even a profile with no datum references controls the coplanarity of surfaces. So what does that mean in the context? Let's look at this. We've got a flatness applied to 3 surfaces, and we've got this dimension that applies in 1, 2, 3 places. That does not control coplanarity, because flatness is an individual requirement. So is parallelism. What you could get with this part are 3 very flat surfaces that have nothing to do with each other. So you could end up with something like this, where the 2 red lines are indicating the total tolerance within the limits of size, and the individual blue lines indicate this 10 thousandths of flatness. Each surface is flat to itself. Now, this might be okay in some applications, but it's worth knowing that that's the requirements you're putting on the drawing. Now, what profile does is control the surfaces to each other. So instead of them being individual, now the tolerance zone goes the full length, and every one of these surfaces must fall within that tolerance. Now, this profile doesn't have any datums on it, so it's not related to anything, but this could be used to control the flatness of the surfaces to themselves within the limits of size like this, or it could be used like parallelism, or it could be used with a basic dimension to control the size, location, and everything else. So that's a really important thing that profile does. It controls coplanarity. So if these 3 surfaces were to serve as a datum feature, you would want to make sure they're coplanar enough so that the part doesn't rock when somebody is trying to measure it. So next up, I'm going to talk a little bit about composite profile. It's a really powerful tool in the GD&T toolbox. It allows you to have a large variation in your location and still control a surface's flatness or parallelism to a very fine degree. So let me show you what I mean. So let's say we've got a really long part, right? So we got a hole on this end, hole on this end. Again, all the details on this part aren't shown. I use this as an example to talk about multiple datum reference frames. It'll work just as well for this profile discussion. Datum A is the large flat surface. Datum B is this surface here. Datum C is here. And we're going to establish a datum D on this side of the part. Now, we're going to use a basic dimension here. Say it's 48 inches, okay? So we're going from datum C to datum D, the overall length of the part. The idea is we would want to have a position for this hole to A, B, and C, and the position for this hole to A, B, and D to make it slightly easier to inspect and functional enough. Okay, our first option, profile to A, B, C, that will establish D just fine. But measuring a profile of 10 thousandths from 48 inches away could be difficult, right? We might want to open up that tolerance to make it easier to inspect. This is the most restrictive we can be, a single profile to our datum reference frame. So why don't we try this? We'll just make it bigger, right? We'll make it a quarter or a 3/4 of an inch. That would certainly be easier to measure, but now this surface could be so rough we might not get a good measurement to this hole, right? That wouldn't be super good. So what we want to do is, right, so that's what we would get with that 0.75, get a very, very rough surface. So what we want to do is allow that surface to be over here, wherever, but keep it relatively, straight so we can measure from it. So the way we're going to do that, we're going to leave this, but now we're just going to measure the flatness of that surface, right? So we've got this 3/4 inch, let's flatten it up. What I've done is made this a composite profile. So one geometric characteristic symbol with more than one segment. Now, in this particular example, 2 single segments means the same thing, but I'll make it composite just to show you the one symbol. Okay, so this 10 thousandths indicates that this surface needs to be flat within 10 thousandths, and it also has to adhere to this upper segment. So what that's going to do to us is flatten that surface up, but it's still free to tilt and move around within this 3/4 inches, and that's exactly what we're looking for there. Now, if we wanted to make this surface perpendicular to B, which is kind of what we want, we would have to do datum B right here first. But with a composite profile or position, we cannot go out of the order of the top datums. Okay, we have to stick with those. So if this is A, B, and C, we have to start with A and then go to B down here. So I'm going to do that. We're going to add datum A. Now it's difficult to see here because datum A is that large surface, but you could potentially, without referencing datum A in the second segment, even the thin portion of the part could be out by 3/4 of an inch, which isn't what we want. So I'm going to skip ahead to datum B here. What that's going to do is snap this into shape. So now we got to be flat to 10 thousandths. We've got to be perpendicular to datum A, which is the largest surface, and perpendicular to datum B. So what that does for us is control the perpendicularity of this surface to A and B, the flatness, but it can still float within this 0.75, which, in my opinion, for the limited function of this part, is a success. Okay, so that's what composite profile can do. Now, normally composite profile is applied to more than one feature, so a pattern of features, but it can easily be applied to a single feature to give the designer more control. Now, another thing I want you to take from this is that when you see a complicated feature control frame, it often means that you have more tolerance because the designer went through a little bit of trouble to figure out where to get some extra tolerance from. It's the easiest thing in the world to slap a profile of 10 thousandths to A, B, and C, or your primary, secondary, and tertiary datums on your part onto a drawing and it's normally good enough. But if you have this, it meant the designer went out of their way to find some tolerance. Now, as far as inspection goes, it's two separate checks, right? So the 0.75 to A, B, and C, and then you essentially check in the perpendicularity to 10,000ths to A and B, but you don't have to reference C. So you don't have to go back over here for the measurement on the second segment. Now, if you measure from A, B, and C, and the surface is good to less than 10,000ths, you only have to do a single check, right? So if you check the bottom tolerance to the top datum references and it's good, then you're done, okay? I know it sounds a little weird, but that's essentially how it works. And if I didn't mention it before, the difference between the composite and the two single segments is essentially nothing in this case. With the two single segments, you can have the datums in a different order if you needed that for some reason, whereas the composite, they need to be in the same order and the same material condition. So if it's a different material condition, it's a different datum reference frame because you're calling out the datum in a different way. So that's it for this video, just an overview of Profile and some of the applications. If you enjoyed the video, please like and subscribe. Check out the channel for more GD&T content. In this video, I'm going to talk about tolerances of position. So there's 6 videos in this GD&T series. We've talked about form tolerances, orientation, runout, profile. What all of these tolerances do, for the most part, now there's always exceptions, is control the surface of a feature. So if you put a flatness tolerance on the surface of something, you're going to run an indicator or run a CMM probe over it to determine whether that surface is within the tolerance zone or out of the tolerance zone. Similar thing with runout, right? You're going to rotate a part and check to see if the surface is located to the axis of the datum, and you're seeing if the surface, the form of it, is circular or cylindrical, depending on the runout tolerance. Now, if we used Profile on something like a hole, we can locate the hole and control the form and control the size. But what we're doing when we do that is we're controlling the high points and the low points of the hole. Let me show you what I mean on the board. So this is a limited drawing, of course. We've got what we need for this explanation. We've got a profile of a surface applied to a hole. Now, of course, it's going to be a basic dimension in this case. We've got 3 datum features and 3 datum references. So what this gives us is a tolerance zone that follows the true profile of the hole. Since it's 3-dimensional, you essentially have 2 concentric cylinders that are located to A, B, and C. It's perpendicular to A and then located to B and C. So what that would look like is something like this. Okay, so you've got tolerance zones where the part has to fit within. So if the part doesn't come in perfect, you could have variation, but you're still looking to make sure none of the points are outside of these tolerance zones. Now this can be tricky to check without a CMM because the implication here is that you need to go inside of this part and make sure none of these low points exceed the tolerance zone of the profile. Now, position is going to work a lot different than this. What position does is separate out these low points that are essentially not functional, right? Nothing is going to mate to these low points. If you put a pin or a bolt or a screw through this hole, it's really only gonna, the high points here, and when I say high points in a hole, I mean these points here, right? What would make it the smallest hole, okay? Position is only gonna worry about these points. The lower points are controlled by the limits of size. So they still have to be checked, but you're just not checking them in the same way you would for a profile, right? Now, one thing position does is separate out the location of the feature from the size. So say you had a hole that needs to take a ground pin and have a very tight fit, but it doesn't matter so much where it is. You can do that with position, where it'd be more difficult to do that with profile and certainly more expensive. And then the other way as well, you could have a really tight location and then a really loose size tolerance if that was necessary. So let me show you what I mean by only controlling the high points, how we're going to accomplish that. We're going to use the concept of the actual mating envelope. I've got another figure on the board. Again, not a complete drawing, missing the basic dimensions, but it has what we need. Now, instead of profile here, I've got a size dimension, a position feature control frame, 3 datum features, and 3 datum references, okay? So I've kind of cheated, you know, this is the drawing, and then this is the part that actually comes out, but it's instructive for what we're going to do here. So how do we decide whether this is within the tolerance zone? So the tolerance zone for position is a diameter, right? We got a diameter symbol here of 30 thousandths, located at the true position, which in this case, even without basic dimensions, we'll get to that later, is going to be on the drawing right where the center mark is. So that's our tolerance zone. Because it's related to datum A right here, that's what gives it perpendicularity. So we're going to project it over here. That's our tolerance zone for position. So what are we controlling exactly? Well, for a hole, we're controlling the axis of the unrelated actual mating envelope. What does that all mean? Well, in order to figure out where the axis of this hole is, we need to decide how we're going to get the axis. And the ASME standard, how we're going to do it, is by using the actual mating envelope, which is, for right now, we're going to say it's outside the material. It's the largest similar feature that will expand within a hole, or the smallest external feature that contracts about around an external feature. So in our case right here, how it's usually done is you go through gauge pens until you find the largest one that will fit through the hole. If it's a large bore, you might need something like a mandrel that actually expands into the hole. But essentially what you're doing is trying to find a best fit with these high points and then the largest cylinder that will fit through there. So you'll end up with something like this. Okay, so imagine we went through our box of gauge pens and we found the one that will fit through just barely, and it won't wiggle around, and then the next size wouldn't fit. That's our actual mating envelope. The axis of that is going to be the axis of the feature, right? Because we only care about these high points, because when this part goes into service, those high points are going to be what's going to stop something going through the hole, whether it's a pin or a screw or a bolt or a mating part. So if we imagine, and I'm going to draw it solid, the axis, the actual mating envelope is the axis of the feature, and now we're just looking to see if that entire axis falls within the blue here, our tolerance zone. Now, it's really not that difficult to do on a plate, and I've made a whole other video about it. Essentially, you're going to measure from here, take half of the gauge pen, go down, and you'll find a point. You'll do the same thing on the other side. You'll take the worst, do a little bit of trigonometry, which I'll show toward the end of the video, and figure out whether it's within tolerance or not. But that's the big difference between position tolerances and basically all of the other tolerances, and that's why some people have difficulty with it, because you're not really measuring all of the feature. You're only considering what really matters, and it's a very powerful thing to apply to a drawing. And then later in this video, we'll get to applying MMC and LMC and how you can get even more tolerance with this concept, okay? So let's get into some of the nuts and bolts of position tolerances. Now, a position tolerance can be applied to two things: a feature of size or a bounded feature. Bounded features are rarely used, and I'll just touch on it, but a feature of size is used all the time. They have two major characteristics. The first being they're going to have a plus or minus tolerance. Now, it's not always with the dimension. It could be, referred to a title block or an associated document, but there's going to be a plus or minus dimension somewhere, even if you have to look for it. The other thing, and of course in the ASME standard is long definition, but basically it's opposing points you're looking for. So a cylinder has opposing points you can measure, whether it's external or an internal cylinder. So, a caliper can kind of measure inside out, or a caliper can measure outside in. So cylinders, spheres, widths, slots, grooves are all features of size. What isn't a feature of size is a chamfer or a fillet, because there's no opposing point to measure. Those would not be able to be controlled in the ASME standard with position. Now in the ISO standard, there's ways you can control surfaces with position, but it's outside the scope of what we're going to talk about today. Now, a bounded feature is kind of a different animal. Essentially, you're using profile with position. It's got to be an enclosed shape, and then you can use position and profile together. It's not a super common thing, so I'm not going to spend any more time than that on it. Now, position tolerances have 3 requirements, things that have to be on the drawing. So the 3 things that need to be on the drawing are 1, basic dimensions, 2, datums, and 3, feature control frames, or at least one of these. Now, a basic dimension can look like this with a box around it, or there can be a note on the drawing that says all dimensions are basic. Datums, now this is the datum feature symbol that identifies a datum feature. The datum feature reference is in the feature control frame. It's a lot of terminology, but you can just call them datums and people know what you mean, okay? And people would say in the comments, datums are theoretical. Yeah, I know they're theoretical, but for normal people, it's okay just to say datum, and people know whether you're talking about a datum feature reference, or a datum feature symbol, okay? Now, the feature control frame, this is what's going to tell us what's going on with that feature and how we're going to interpret it and how we're going to inspect it. These elements need to be there, and they're things you're going to look for when you're interpreting or applying the position geometric characteristic. Now let's look a little bit more closely at the feature control frame, specifically for position. So the feature control frame, typically for position, this first symbol is our geometric characteristic symbol, in this case, position. The second thing we'll have is the shape of the tolerance zone. We can have diameter, we can have a spherical tolerance zone, or there could be no symbol there if we're controlling a width, so a center plane, right? Next is the value, or the tolerance value. This is given as a total. So when it's applied to a diameter, that's the diameter of the tolerance zone. When it's applied to a sphere, it's the diameter of the sphere. When it's applied to a width, it's the distance the 2 planes are apart in which the center plane of the feature must lie. Next up, material condition modifiers. Now, position is applied to features of size, so there'll either be a symbol here. If there's not a symbol here, then it's regardless of feature size. That's rule number 2 of the ASME standard. It just means that no symbol, the tolerance is always 30 thousandths. With the symbol, the tolerance can change depending on the size of the actual feature, and I'll discuss a little bit more later. Next up are datum references, or primary, secondary, and tertiary datum. In that order, it doesn't matter what letter of the alphabet they use. Now, most of the time people use A, B, and C, but it doesn't have to be. You can use any letters that don't look like numbers. So you can't use I or O or Q, but any other letters you can use. Now, depending on the datum feature, sometimes these will have material conditions. Now, in this case, A doesn't have a material condition, B does. B applies at MMC, which can make gauging easier. Now, if the datum feature is a feature of size, again, just like the tolerance, it's going to be regardless of material boundary, which is like analog to regardless of feature size, unless you've got an MMC or an LMC symbol in there, okay? So the tolerance in the feature control frame, as I sort of mentioned before, can control a couple of different things. I would say the most common thing is the axis of either an internal feature like a hole or an external feature like a cylinder. Now, it can also control a center plane. when it controls the center plane, it will not have a diameter symbol there, and I'll put a figure on the screen for you. It can be used to control the width of something to another datum, or it can be used to control a slot or a groove. And the idea here is that the actual mating envelope for an internal feature, say we've got a slot, right? So this is the perfect part, this is the actual part. The actual mating envelope is two parallel planes that expand until they touch the high points. So imagine you stuff a gauge block in there, right? You go from a small gauge block to a large one and find the largest gauge block that would fit. And then the center plane of that gauge block is the center plane of that feature. And it would be need to be between two parallel planes this distance apart to whatever datums are there. So you'd end up with a situation. So you'd end up with a situation where you have two planes. Of course, they're 3D. They go all the way through the part. And then you want to see if the center plane of the features within those two parallel planes, this distance apart. Now, practically on a plate, you know, if it's a small enough groove, you just get a gauge block, you can flip the part over and use a height gauge to measure either side of this, take half of that, you can basically figure out where you are. This is less common for position, but it's still, you know, out there controlling the center plane of a feature. The next is controlling the center point of a feature. This is used for spherical features, and you would see an S in front of the diameter symbol. This would be used, say, the only example I can ever really think of is like a trailer hitch, right? You've got a kind of spherical shape, and you're looking to control the location of that sphere. Now, as far as how to inspect that, how to get the actual mating envelope of a sphere, I mean, you know, theoretically it would be a perfect sphere that collapses onto the existing sphere. I don't know how you'd really do that on the plate. I know a CMM machine can do it with no problem, so I'll leave it right there for you. I would say it's a less common use of position. Now, there's another use, you know, other exceptions. You can use position, like I mentioned before, with profile and create a boundary. I'll leave that to another video. The use with the axis and the center plane are the very most common, so that's what I'm going to spend time on right here. So let's move into talking about some of the particulars. Now, the basic dimensions always come from datums, which come from datum features. They're going to locate the true position. The true position is the theoretically exact location of the center of the tolerance zone, whether it's a spherical tolerance zone, a cylindrical tolerance zone, or two parallel planes. Now, the term true position is often used, you know, you might say, hey, this is a true position tolerance. That's not totally correct, but it's out there, so I probably wouldn't give anybody a hard time for saying that, but technically this is a position tolerance. The true position is the location, perfect location of the tolerance zone. Now, position tolerances only work with datums. You have to be measuring from somewhere. So position tolerances locate things. In order to locate something, you have to, you know, compare it to a different place. Let me show you what I mean on the board. So I've got a sketch on the board here. Again, incomplete drawing, but we've got a position, we've got datums, and we've got basic dimensions coming from the datum. So this is all on the part. Now, if we go to inspect this, we could make a gauge or put together, you know, angle blocks to kind of form a temporary gauge that would look something like this, right? So imagine you just take three perfect blocks and stick them together. So you have a nice 90-degree corner here, and you've got your datum simulators, places to measure from. Now, the idea with this setup here is that you're going to put the part in there and be able to measure from these surfaces, not from the actual part surface. The reason is that if the part comes out like this, it matters whether you measure from right here or you measure from this 90 degrees here, right? So if I put the part in like so and measure the location of the hole in this direction from the datum simulator, I'm going to get a different answer than if I push the part up against the datum simulator and measure it like this. That's what the order of datums gives you. So we're going to make in this case, from 3 points of contact with A, which means we'll push it up against this large flat surface. 2 points of contact with B, which means we'll push it up against datum simulator B, and it only needs 1 point of contact to lock translation for C. And then we're going to make all of our measurements from there. So the way I like to think about it is this doesn't move. The part moves around this. Now, our true position shown right here also doesn't move, right? You kind of imagine the part fitting around the true position, and then it's very important that we always make our measurements from the datum simulators, the inspection equipment. That gives you repeatable results. For the most part, your actual measurements, when you're doing this on a plate, right, you'd probably be using a height gauge measuring to the gauge pin. Now, this would take a very large gauge pin, but imagine we put a gauge pin in here, we put it in the fixture, we put our height gauge on this surface, or however we need to do it, we measure to the top of the pin, we take half of it, that gets us the location in one direction. We can flip the whole fixture over and get the location in the other direction. So we're going to get repeatable results no matter how far off the actual part might be. Now, you don't have to do this way on a surface plate. A CMM will do it perfectly fine. There can be issues if you try to do it with a height gauge. Say you take a electronic height gauge and you take a point here, here, and get the middle. It's all about how you actually set it up on the plate according to the datum references. Again, the datum references don't have to be in this order. It could be ACB, and then you'd set the part up differently. There can be different datum reference frames on the same part. So if this part had multiple holes and one of them was ABC and one was ACB, you'd have two different setups on the exact same part. And then the next thing is, sometimes people ask, okay, well, what's A doing, right? We're not taking any measurements from A. And you sort of are. It depends how thick the part is. So a really thin part like this, you wouldn't typically flip it over and measure the gauge pin on both sides. But if a part is thick, you're going to flip it over and measure it on both sides. A is controlling the perpendicularity of the part. So if you imagine our round tolerance zone right there, that tolerance zone is also perpendicular to A in almost all cases. Okay, so that's what A does in this case, or the primary datum feature. So let's chat a little bit about material condition modifiers. In this case, it's a position, feature of size, no material condition modifier. It means that this applies at RFS. So what exactly does that mean? If we make a little chart, it just means that if the hole comes in at MMC, the smallest hole, 0.98, you have 30 thousandths position. Comes in the middle, 30 thousandths position. Comes in at LMC, the largest hole, 30 thousandths of position. Okay, so pretty straightforward stuff. It gets expensive to do it this way because a lot of times, you know, when you have a clearance hole, it's okay for the hole to get bigger. That doesn't matter so much. You just don't want it to get smaller because something, whatever's fitting through it, might not fit through it. So we have a solution for that. It's called the concept of MMC. So what MMC does is that if the feature comes in at the MMC size, you only have 30 thousandths of tolerance. If it comes in at any size going away from MMC toward LMC, so in this case, if the hole gets bigger, you get more positional tolerance equal to the difference from the size it actually is from the MMC. So let me show you what I mean in this handy chart. So at MMC, we have 30 thousandths of tolerance. That doesn't change, right? 30 thousandths at MMC. But if the hole comes in 20 thousandths too big, we can add that to our existing position tolerance. So in this case, we would have now 50 thousandths of position tolerance. As the hole gets bigger, you get more positional tolerance. If it comes in an LMC, we just subtract the LMC from the MMC, we get 0.4, we add that to the 30 thousandths we already have from over here, 70 thousandths. Right? And that's what MMC does in this situation. For a hole, for an external feature, it gets flipped. Now, next up, we're going to talk about the concept of virtual condition. In this case, it's just the smallest the hole can be, taking into account the size of the hole and the geometric tolerance. So visually what I mean is, say a hole in a part comes through like this. If we have a pin that has to be perpendicular to this surface and fit through the hole, there's a limit. The size of the hole matters and the position of the hole matters, right? So this cylinder right here, if it's perpendicular to this surface, which is usually like a datum A or a primary datum, and we want it to fit through the hole, that's going to be smaller than either the size or the geometric tolerance we're considering. So this is known as the virtual condition, or it could be a worst case condition. So how we get this, what this diameter of this is supposed to be, is by subtracting any of these two numbers horizontally. So we're going to get 0.95 across the board. That would be the diameter of this, okay? It's a very, very handy thing, because if we can prove at inspection that a pin of 0.95 will fit through that hole when it's perpendicular to A and then, located everything else, whatever, we know that feature is good. It'll meet its functional requirement. We can't do this with RFS though, just MMC. Now, so this is handy at inspection. We can have a hard gauge that can make sure it can verify that this position tolerance is good. Then you just have to check the size tolerance and make sure the hole isn't too big. Now, I'm going to skip LMC. I've got other videos about that. Basically, LMC is opposite, right? As the hole gets smaller, you get more position tolerance, whereas at MMC, when the hole gets bigger, you get more position tolerance. LMC is used when you're protecting wall thickness, when you have, like a spokes in a wheel, and you want to make sure those holes don't get too big to where they, cut into existing material. That's where LMC is used, but this is not that common, so we'll go ahead and move on. So we've talked about what position is, the kinds of things it controls, what we're looking for. Now let's dive into how you're actually going to interpret the data you get. So if you inspect something on a surface plate, you're essentially going to get X and Y locations for the actual mating envelope. Now, these numbers are not going to correspond with this diameter. Let me show you what I mean. So say we've set the part up on the plate and we get some measurements. So what I'm saying here is you get in the setup and you're going to measure to your gauge pin from one side, and then you're going to have to flip it over and measure from the other side. So you subtract half of whatever the gauge pin is, and you're going to end up with something like this. So from the previous drawing, our basic dimension was 1 inch. So we're going to say we're 10 thousandths off in this direction and 20 thousandths off in this direction. Now, we want to compare that to the true position, right? The true position is somewhere in the middle of the part. So we want to find the variation from the true position. This is the variation from one of the datums. Now, how we do that is we're going to subtract the basic dimension, or the drawing dimension, from what we actually measured to get our variation in x and y from the true position. So in this case, we've got positive 10 thousandths and negative 20 thousandths. That doesn't get us any closer to knowing whether it's within tolerance or not, because these are the x and y's, this is the diameter. What I mean, if I plot this on a Cartesian coordinate system, we're plus 10 thousandths in x and minus 20 thousandths in y. What we want to know is if this point that we measured falls within a diameter of 20 thousandths on the true position. So the center of this Cartesian coordinate system is the true position. So we can draw a circle, and you can graphically do this, right? It's called paper gauging. You could, if you have a good protractor, you can grid this out, draw a circle, and see if the point is within the circle or not. But that's probably not super common to do it with pen and paper. I mean, you can do it with Excel. The way I'm going to show you here is to convert this point into a diameter so you can find out how much positional tolerance it actually used. So what we're going to do here is find, there's going to be a triangle in here, right? A right triangle. Pretty straightforward to figure out what that is. We know where the center is, we know where this point is, and then we're going to take the hypotenuse of that triangle and double it to give us the size of the circle that point consumes. Now, the way we do that, so we're going to enter it into this formula. So the variation in x squared plus the variation in y squared, whole thing, take the square root of that, times 2. The times 2 is this, doubling the hypotenuse. This thing right here gives you the hypotenuse of your triangle. Double it, gives you the diameter of positional variation. So let's go through the math real quick. So the first thing we do, we insert their variation into their respective places. We square each one of them separately. So it turns out it doesn't matter that this one is negative. So we're going to get 1/10 of a thousandths, 4/10 of a thousandths. We add those together first. Then we take the square root. We get 0.0223, multiply by 2. It gives us the total consumed positional tolerance is 44 thousandths. We compare that to our available tolerance, and we know that this part has failed, right? This is not an acceptable place for this hole to be positionally. Now, we might have a way out. Whenever we have the MMC symbol, right? Remember I mentioned before, if the hole gets larger, you get more positional tolerance. So with RFS, you don't really care how big the hole actually is as long as it's within the limits of size. But with MMC, you want to actually find out how big that gauge pin was because you need to know the size of the hole, and I'll show you why in a second. So let's say our hole came in at its largest size, 1 and 20 thousandths. That means that we're going to have additional tolerance. So how much additional tolerance are we going to have? In this case, for an internal feature like a hole, our bonus tolerance is the actual size of the hole, so the size of the gauge pin we use to check it, minus the MMC size. So in this case, we're going to say it's 1.02 minus 0.98, the actual size of the hole. So that means we have 40 thousandths of potential bonus tolerance. Well, it's not potential because we know the size of the hole, so it's our actual bonus tolerance. Now, we can add this bonus tolerance to what we already have. So that's going to be our total allowable tolerance. Total allowable tolerance is the specified tolerance plus the bonus tolerance, okay? So in this case, 20 thousandths plus 40 thousandths is 60 thousandths. That's how much tolerance we have. We can compare it to our calculation over here. Because of the MMC symbol and that the hole came in large, this part would be acceptable at this point. Now, you have to go do this for every hole. If you're lucky, the same gauge pin will fit in every single one, but if you're inspecting, it's something you want to keep track of. Okay, so that's how MMC can help you. Say the hole, we checked the part and the hole came in small, you could go back and drill or bore that hole out again and then send it back to inspection. So it gives you the capability for rework. Whereas if we didn't have the MMC symbol, there'd be no, unless they put the MMC symbol in there and made the hole bigger, but that's, you know, more of a drawing change, right? So that's how the system actually works. You're taking X and Y coordinates, converting it into a diameter. Another way of thinking of the diameter is that it's the smallest inscribed circle, so it has to touch the actual point, and it's centered on the center of the true position. Now, in another video, we'll talk about composite position. Basically, what composite position can do is release the requirement for the circle to be centered on the true position. It can kind of float around and get a best fit with several holes in a pattern. So I'm going to make a part 2 to this video. I think this is already getting pretty long, but this is the basics of true position. Now, obviously there's more to it than this. You know, if you go through the ASME standard, just pages and pages of really obscure stuff, but this is what I think is going to help you, especially if you've heard of true position, you're just trying to learn. Hopefully you found this video helpful. If you enjoyed it, please like and subscribe and leave a comment down below, and keep a lookout for a second video on this topic coming soon. In this video, I'm going to go over some advanced applications of position. So we're going to cover things like applying position to threads, patterns, applying position without any datum references. There is one exception where you can do that. And then things like conical tolerance zones and repetitive patterns of features with repeated datum reference frames. Some of this you may never see your entire career. It's good to know, especially if you want to take the senior certification exam, because these are the kinds of questions they try to, get you with. In the ASME standard, there's no relation between how often something is used and how important it is and how much is written about it. So there could be something super important that only has like one paragraph, or something that's barely ever used that has like 2 pages devoted to it. So I'm going to try to treat all of these topics equally, even though you might not use them or see them very often. Now first, let's get into applying position to threads. So position can be applied directly to threads to control the location of the feature. Now, it's important the ASME standard recognizes the feature related to threads as the pitch cylinder of the threads. That is what you're controlling with this position tolerance, not the major diameter or the minor diameter by default. Now what that means inspection-wise is you need some somewhat special equipment. Now there's special thread gauges made for this, but you have to try to find the pitch cylinder, so kind of the middle between the tops and the bottoms of the threads. And this makes sense because that's what locates threads. You could have a thread like this. Our pitch cylinder is determined off the pitch of the threads. If somebody came in and they ground the tops of the threads like so, right, you take some off the top of this side and some off the top of this side, you'd get a different answer if you gauge this thread by, putting it in a collet or a chuck. It'd tend to tilt a little bit, right? So the major diameter doesn't always locate threads very well. But it's much easier to inspect, right? To grab, to find what the axis of this feature is. If you're looking at the major diameter, you just clamp it in a chuck or a V-block or something. But if you need to find out what the pitch cylinder is, you need a special thread that closes down on the feature to locate this pitch diameter, which is what locates the actual axis of the thread. Now, that being said, as a default requirement, you have to get the pitch cylinder to find out if this thread is within its position tolerance. But you can very easily, underneath the feature control frame, indicate that this should be inspected at the major diameter. The thread might not locate as well, but it's much easier for inspection to do it. Now, that's a conversation you have to have between design and inspection about, what kind of requirements you're looking for, but that does make inspection easier. We can do the exact same thing for a threaded hole. Now, some people might say you can inspect this with the largest pen gauge that will fit through it, just like you're inspecting a regular hole. But since you're really looking for the pitch diameter, the largest pen gauge is not a representation of the actual mating envelope of that thread. You're looking for the pitch cylinder. You can remedy this in the design room by just indicating minor diameter beneath the feature control frame. Now, there's an argument that this should be the default requirement, and then that you should have to go through extra effort in the design room to call out the pitch cylinder. But the ASME standard typically defaults to the least fun option or the safest option. It's kind of like how things default to regardless of feature size, which is more difficult to inspect, but it's typically gives you the tighter tolerances. Okay. The next thing is, there's an argument here as to whether you should apply MMC to threads. I would say normally you shouldn't, because if the thread comes in small and you want to take advantage of that MMC, one, there's not that much difference between the largest the thread can come in and the smallest it can come in, maybe thousandths or two, depending on the size of the thread. And it's more difficult to find that out than it is to inspect a thread at RFS. I think it's fairly common to always call threads out regardless of feature size. If your company uses MMC on threads and you inspect that way, I'd be glad to know in the comments. Please let me know down below. So next I want to move to counterbores. Now, normally a counterbore is called out with a single position tolerance that applies to the hole and the counterbore. Let me show you what I mean. So the most common way a counterbore is put on a drawing is like so. We've got the diameter of the through hole, which always comes first. We've got the counterbore symbol, and then the diameter of the counterbore, followed by a depth either below it or beside it. And then we've got a feature control frame that indicates both of these are going to be to whatever the datum reference frame is. I've omitted it in this figure, to 14 thousandths. So the same tolerance zone for both of them from the same datum reference frame. Essentially, the axis of both features must fall within that tolerance zone, okay? Now, this can be fine, but it typically is more expensive. Typically you want a kind of small hole because you need bearing surface for the underside of a bolt head, but often the counterbore could get larger. Like that wouldn't affect the design, unless it's running up into a thin wall condition or something. But typically the counterbore can be bigger than, it can grow more than the hole can, right? If the hole gets way too big, you're not going to have any room for bearing surface for the bottom of the socket head cap screw or whatever you're using. So the way we accomplish giving more tolerance to the counterbore is by identifying the hole with the same 14 thousandths that we would have gotten from a calculation of some kind. And then we can apply a separate position tolerance to the counterbore and make it much, much larger. Now, typically you use MMC on both of these, but you could use RFS on this one and MMC on this one, because the counterbore really is usually just a clearance feature, as long as it's not going to get too big and run into some other feature. Again, it'd be nice if this was the default for counterbores, but people see this on a drawing and they kind of freak out and just assume it's going to cost more. Typically, this would be the cheaper way to go. When you inspect it, right, you can inspect them both the same way, right? You really should inspect the counterbore and the hole separately, right? Unless you have some gauge that can expand in both at the same time and capture both axes. And that's really not what you want either. They're really separate features called out with the same feature control frame. You could really think of this feature control frame as being repeated instead of it being, a control that controls both of them at the same time. Now, this controls them separately. So at inspection, say you get a gauge pin, you put it in here, you see if it's good, get a gauge pin, put it in here, see if it's good. You do the same thing down here, you just have more tolerance for the counterbore, okay? And then the tolerance zones for this counterbore feature would look like so, right? You have a small tolerance zone for the through hole, then you have a much larger tolerance zone for that counterbore feature. Now, there's another way to do this where instead of relating everything back to one feature control frame, we can actually relate the counterbore to the hole individually. So we're essentially going to treat every single hole, if there's multiple, as a separate datum. You don't have to make each of them a datum and use every letter in the alphabet. It's just understood that you're going to do that by writing the term individually underneath the feature control frame. Let me show you what I mean. All right. So in the example here, of course, this is an incomplete drawing, but I tried to put all the information we need. We've got a hockey puck shape with 4 counterbore holes in it. Datum A is the flat on the back of this. Datum B is the outside diameter. We'll start on the front view. We've got 4 holes positioned to A and B, so they form a pattern. Now, they're counterbore holes, so we've got to take care of that counter bore. And I should make this arrow, it should go to the inside hole because that's what it's referring to. Now, in this partial section view, we've got 4 times, so one for each of the counterbores. Whatever the diameter of the counterbore is, a position. But now we've got datum C as each of the counterbores, but they're going to be repeated. So it's like datum C 4 different times for the purposes of inspection. It's not datum C is a pattern of 4 holes. It just gets repeated, and you know that because you'll put a note that'll say 4 times individually. So the advantage with this is the counterbore stays with the hole. So if you needed to give the position of the holes a large tolerance, you would be sure that the counterbores would follow them around. If you gave both say we did it the way we did a minute ago, where you have a position controlling the hole and the counterbore, if you make the position of both of them very large, you could get something like this, where they're not coaxial at all. You could get the same thing when you apply 2 positions separately to the hole and the counterbore. This keeps the counterbore with the hole. For inspection, it can be a little bit more difficult, but it's a tactic that you should be aware of. So this is the other way of doing counterbore holes. These are the 3 ways it shows you in the ASME Y145-2009 standard. So let's move on to patterns. There's a couple different patterns. Probably the most common you see out there is a rectangular pattern, where you have like a square part and basic dimensions coming from planar datums. We also have round parts like this hockey puck that might have a polar coordinate system, so angles and a bullet hole circle, or a rectangular coordinate system on a hockey puck shape like this, where we have features coming from the dimensions coming from the center lines. Let me draw a few examples of those, and we'll talk about some of the differences.
So let's dive into patterns. Patterns are very common on drawings where you have one diameter dimension for several holes that are all the same size. In other situations, maybe you have slots or other repeated features, saves room in the face of the drawing. So let me give you a couple examples. All right, so a couple words about different kinds of patterns. Usually with position, the way you put the dimensions on there doesn't really matter that much. Oh, let me give you an example. With this pattern, we've got 4 holes, a typical block with holes in it, good GD&T example. Datums A, B, C, 4 holes, position tolerance, they're all related back to the ABC datum reference frame. So every hole can be checked separately as long as it's in the same datum reference frame, the same setup that you would do depending on what you have around. You could do it with angle blocks and gauge pens and a height gauge, or you could do it with a CMM, all sorts of different things. But essentially, your tolerance zone stays fixed to the datum reference frame. Now, with the basic dimensions, you can actually repeat them. So say we had an overall basic dimension here, we could just as easily come from this edge to here. Then it would mean the exact same thing for inspection. As long as there's basic dimensions linking basic dimensions, you're good to go. It's just a matter of preference when you're drafting. Now, normally people are used to seeing it, this dimension for this hole right here, but you don't have to do that. You could go all the way up here and then come back. It means the same thing, because the basic dimension is the theoretically exact location of the tolerance zone to the datum reference frame. So if you make a mistake and if you have 3 basic dimensions, right, with plus or minus dimensions, this would be over-defined. I wouldn't really recommend doing it with basic dimensions because people are going to not like it. But as far as inspection goes, it's theoretically perfect anyway, so there's no tolerance stack up here. Again, don't put this on a drawing because people will complain, but as far as inspection goes, it wouldn't make any possible difference, right? Now, with this particular one, like I said, all the tolerance zones are to A, B, and C, the datum reference frame. You could have a composite position where you release that requirement. You could let tolerance zones, smaller ones, float within these larger tolerance zones away from the datum reference frame, right? With the composite position, you're in the lower segment, you're not going to be measuring from the theoretically exact location of the hole to the datum reference frame. You're only measuring this one right here, right, to the holes and maybe an orientation. Let's move to these. There's 2 basic ways to do patterns of holes on like a bolt circle. The first is to do an angle and a bolt circle, both basic, right? In this case, your tolerance zone for position, and I didn't put the feature control frame, but just assume it's a position just like this, right? You're gonna get a round tolerance zone at the true position, right? I didn't put any datums or anything, but the important thing, round tolerance zone. If you do it like this with coordinate basic dimensions, right, you're gonna get the exact same thing, right? Round tolerance zone at the true position. It makes no difference, right? As long as the math is correct, right? As long as you figure your angles and everything correctly, and it's good in CAD. It doesn't make any difference for inspection. Whereas, if these are plus or minus dimensions, you're going to get different shape tolerance zones. If this was 120 plus or minus a couple degrees, and then 2 inches plus or minus something, you end up with a wedge-shaped tolerance zone. I actually have a General Motors drafting manual from the 1950s where they basically said, don't do this, only do this. And most of the examples in that drafting manual are like that, right? So even way back then, they kind of recognized
the wedge-shaped tolerance zone is not good. At least a square-shaped tolerance zone is better than that. The other problem with this, with the angle, the further you get away from the center, the further it can be off. For a simple part like this, it doesn't matter, but imagine you have a part with, rings of holes. The further they get away from the center, the more they can be off in the angular direction. Okay. Let's move to something called bidirectional position tolerancing. When you put the diameter symbol in the feature control frame and apply it to a cylindrical feature, it indicates you have a cylindrical tolerance zone. It doesn't have to be, though. You could have a square or a rectangular tolerance zone. Now, why would you want to do that? Well, there could be a situation where it's okay for a hole to be, further to the left or the right, but not up or down, and you could apply that tolerance that way. Say you have a slotted part fitting on top of a part with a hole in it. It might be okay for that hole to move in one direction a lot and the other direction not so much. Let me show you what I mean. Okay, so I've got two things going on here. We've got a bidirectional positional tolerance zone on a round hole. Now, why in the world would you want to do this? Well, it gives you a rectangular tolerance zone. So the hole's going to have more tolerance in one direction than the other. Now, I wouldn't recommend using this unless there's like a clear need for it. Say you do a stack up and you need it for some reason, but it is available, and this is somewhat what it looks like in the ASME standard. Now, we've got a position of 30 thousandths in this direction, and then a position of 60 thousandths in this direction. What that's going to give us is a tolerance zone that looks like so. Whenever you do this for this example and the next example where I actually show it, you typically want to apply a perpendicularity to the feature, especially if it's a hole, because the axis could be tilted 60 thousandths, so it could be way out of whack when you're just trying to control. When you make the location that big, you also allow the orientation to get that big as well. So you might want to, and I can just go ahead and draw it up here. Might want to apply a perpendicularity to that to make sure the hole stays straight, but it could go further this way and this way than it can this way, okay? Now, here's another larger example. This is with a circular pattern, right? So it's kind of like polar coordinates. We've got a basic dimension for this bolt circle. Since these holes are on the center lines, we're going to assume it's 90 degrees basic. Right, so that's what controls the left and right, the dimension that controls it. Now, of course, as with all of these, they're not fully complete. But we've got 20 thousandths that controls how far the hole is away from the center, so this direction. Then we've got 80 thousandths that controls basically the angle, how far it can be away in this direction. And then again, we've got this perpendicularity to control the orientation of each hole. One use for this that I can think of is, say, this plate fits below a plate with slotted holes, right? So when you're fitting a bolt through, it might not matter as much whether this is in tolerance in this direction, but it does matter in this direction, depending on how the slots are tolerance. Now, like I said in the beginning, this isn't stuff you necessarily need to use, but it is there. And if you want to get deeper into GD&T, this is good stuff to know, especially if you want to take the certification exam. This is the kind of stuff they like to throw on there. Now, let's move to the conical tolerance zone. So this has been in the ASME standard since at least the 1973 version. There must have been some company that's just desperately wanted it, and some companies that still use it for something. I've never seen it on a drawing. If your company uses it, please let me know in the comments. I'd be super curious to know. It's meant for long holes where you have a one position tolerance on one end of the hole and a smaller position tolerance on the other end of the hole. Let me show you how it's supposed to look on a drawing. So in the ASME standard, this is called closer control at one end of a feature. It really is only like a paragraph and I think only one figure. And like I said, I've never seen it on a drawing. This isn't really supposed to be used for conical features. It's really for cylindrical features that have a conical tolerance zone. If you're trying to dimension a conical feature, I just use profile of a surface. So what we've got here is a long tube with a hole in it. We've got datum A is the outside diameter, datum B is right here, and what we're saying is whatever the position at surface H is, it's going to be 30 thousandths, and it grows to 90 thousandths at surface G. So if we drew that here, we'd start with 30 thousandths. Right. 30 thousandths at surface H, 90 thousandths at surface G, and the axis of the feature must lie within this conical tolerance zone. Okay, so it could be, you know, it's got to be close on this side, but it can be further away on this side. As far as inspecting at the plate, I'm not sure. You'd have to find a really long gauge pen. I assume you just get your gauge pin in here as far as you can and check the position to A and B, and then just do the same thing on the other side, okay? Next up is position tolerances without datum references. This can only be used in one situation as far as the ASME standard is concerned. It can only be used in one situation with coaxial cylinders. They can be the same diameter or a different diameter, but you're essentially slapping a position on there to establish a relationship between the two cylinders, or two or more. It doesn't have to be two. Let me show you what I mean on the board. So let's start. I'm going to give you a couple examples here. This is the way I would not recommend to do it. We've got a barbell shape with a hole going through it, a position on that hole to the two outside diameters. Now, the simplest thing we can do is say 2 times those diameters, make that datum A. The problem with this is that rule number 1 there's no relationship between in rule number 1, there's no relationship between features. It's only individual features have to be perfect. So if this cylinder is, you know, not coaxial by 1 thousandths, is that good or is it not good? If it's not coaxial by 50 thousandths, is that good or not good? This doesn't help us solve that problem. So we definitely don't want to do that. What we could do is use our continuous feature symbol. That would establish a relationship between those features. It's essentially saying treat these two diameters like there's no gap in between them. So treat it like one feature, easy enough to simulate that. Now, usually this is going to be good enough. But say this part, its only job is to slide into another part, and you don't really care how much wiggle there is in the parts, right? So this slides into a hole, and you don't care if there's any excess wiggle. Well, this is going to limit you just a little bit compared to if you use this concept called, you know, position tolerance without datum references. Now we're relating these two diameters with a position tolerance with no datum reference. So we're essentially saying they're related, but now we can get a material condition involved. So now we could say it's got to be within whatever at MMC, but you're going to get bonus tolerance if these two cylinders come in small, and it's still going to fit through whatever you want it to fit through. So if you can accept these two cylinders becoming smaller, this might be the way to go. Now, you could also apply, you know, total runout to these, but then it's kind of the same thing as a really tight size tolerance. You're not getting the benefit of an MMC call out. If the diameters are a different size, say this one is larger than this one, you would write two coaxial features underneath it. And for a lot of the things I've talked about in this video, don't take what I said and put it on a drawing. You want to look this up in the ASME standard, because some of these things are things people don't see all the time. So you want to make sure you're sticking pretty close to the ASME standard. If your company uses this a lot, then by all means, go for it. But if you're putting it on a drawing for the first time, I would definitely look at the figures and try not to stray too far away. For example, this is what it says in the ASME standard, 2 coaxial features. I wouldn't mess around and write, 2 coaxial cylinders, right? Because whoever sees this has probably seen it for the first time. You're going to open the ASME standard, and it's not going to be the same thing. So you could introduce, room for error in that way. Okay. So the last thing we have to talk about in this video is a repetitive pattern, repeated datum reference frame. So this is a common thing in something like an instrument panel. So say you've got, not for a modern car, but like an old-timey race car, you're putting a speedometer in, you've got the bezel, and then you usually have 2 studs or something that's going to fit through 2 holes. Well, that pattern, that feature, is going to be related to the center bezel and the outside, but not any other instruments on the panel. And we can reflect this with GD&T. Let me show you what I mean. Okay, so this is a repetitive pattern. Like I mentioned before, say it's a dashboard for a bunch of speedometers or tachometers or whatever instruments. Doesn't have to be a car, it could be a factory setting, right? So we got a hole for the center of the instrument, and then the instrument will come with 2 studs that have to fit through 2 holes, and we'll put bolts on the back. So it's important that these are relatively in the right place, right? We don't want them off by like inches or anything. But it's more important that these 2 holes orbit this hole in the middle. That's what we're really looking for. Say if this big hole is off by like, 1/4 inch, is it really a big deal? Are people going to notice? We're just spacing instruments out, okay? So what we're looking to do is control these 2 holes to this big hole very tightly, but to allow each of these little planetary systems to kind of float around a good bit for ease of manufacturing. If you think of somebody making this, right, maybe they're only making one and they're at a punch press and they're just doing each pattern one at a time. They're going bang, hitting one, then the other, then the other. It doesn't really matter how they make it, but it's probably easier to make these 3 in line than it is to make all of these, perfect. All right, so how we're going to accomplish this, I omitted the basic dimensions, but they would come from the datums as, they should. Here's a detail view. We're going to identify these 4 big holes as positioned to A, B, and C, and we're going to make that datum D. Now this can be a pretty loose tolerance, right? We're just controlling where the big holes are. As far as the location, right, they can be pretty far off and our instrument is still going to fit through there. But we couldn't apply that big tolerance to these little holes because if they're off, right, these studs won't fit through at the same time as the instrument itself and the other stud, okay? So how we accomplish that, we're going to do 8 times all these little holes. This first feature control frame, this is a 2 single segment position. It could be written as 2 separate feature control frames. This isn't composite. We're just applying position twice. The first one is going to control all of the little holes to A, B, and C. Now this one can be somewhat loose. The second one is going to control the holes basically orbiting the big hole, right? Oh, the datums are only A and D. There's no rotation involved because we're not relating either B or C, right? So we're really just controlling the distance. The little hole can be from the big hole, but not any kind of rotation. That's what this larger tolerance is going to control. So it's a little tricky, right? This can be pretty big, but this second one is always going to control the distance from here to here. which is what we want for the part to function correctly. Okay? So datum A is the big flat surface, datum D is this hole right here. That is a repetitive pattern with a repeated datum reference frame. Now, this isn't the only way to write it. I ran out of room, but in the actual detail view, I could say 4 times detail A. And then I would write 2 times these 2 holes, and then 1 time this big hole, and then it's understood that the whole detail is repeated. I think the ASME standard in 2009 kind of messes this up in the individual section where it's talking about datums individually. It shows it as, say it's got this, it shows this, and then shows the detail view as also being 4 times. But when you repeat a detail view, you're repeating all of the features within it. I hope you enjoyed it and learned something new about GD&T if you've already been using it for a while, and if you haven't, it's good stuff to have in your back pocket, especially if you ever want to take the certification exam. If you liked the video, please like and subscribe. Leave a comment down below.